Something just appeared between 3I Atlas and Earth, and nobody saw it coming until 2 days ago. On November 2nd, Russian astronomer Gennady Borisov, the same man who discovered the second interstellar object ever recorded, found something new. A comet. But not just any comet. This one sits in a position that defies comfortable explanation. Its designation is C/2025 V1 Borisov, and as of today, November 7th, it occupies a space in our solar system that has ignited a firestorm of speculation across every corner of the internet, where people still dare to ask difficult questions. The object exhibits a defined nucleus, clean, compact, visible. But here is what makes your skin crawl. There is no visible tail. Comets have tails. That is what comets do. They bleed gas and dust as they warm, painting streaks across the sky that point away from the sun like cosmic windsocks. V1. Borisov has none of that. Just a tight, bright nucleus sitting quietly in the dark, positioned almost exactly along the line between 3I Atlas and our planet. Let me say that again. This object appeared directly between the most anomalous interstellar visitor in recorded history and Earth, and it showed up with no tail, no coma that anyone can see clearly, just a core. A core that someone noticed only because Borisov, with his custom-built half-metre telescope in Crimea, happened to be scanning that exact patch of sky on the night between November 1st and 2nd. The Minor Planet Centre issued the formal circular on November 5th. 10 observatories confirmed cometary activity. 10 separate locations around the planet all saw the same thing, a fuzzy something with a faint coma roughly 1.5 arcseconds across, and a stubby tail stretching 7 arcseconds toward position angles 250 to 260 degrees. Its brightness measured at magnitude 12, dim enough that you would need serious equipment to spot it, but bright enough that it should not have been missed for weeks if anyone had been looking in that direction. But here is the thing. Nobody was looking there. Everyone was watching 3I Atlas. The interstellar comet dominated every telescope schedule, every observation window, every press release since July. And while the world fixated on the visitor from beyond, something else slipped into the space between. V1 Borisov made its closest approach to Earth on November 11th. That was 4 days ago. At its nearest point, it passed within 0.69 astronomical units, roughly 103 million kilometres. Not close by cosmic standards, but close enough to matter. Close enough that if this object had any interest in studying us, in positioning itself for a better look, this would be the geometry to do it. Now here comes the theory that has every amateur astronomer and professional contrarian on the internet vibrating with barely contained hysteria. What if V1, Borisov, is not a comet at all? What if it is exactly what Avi Loeb theorized 3I Atlas might deploy? A probe. A smaller craft released from a larger mothership, sent ahead to scout or study or simply observe from a vantage point that the parent object could never reach. Think about the timing. 3I Atlas reached perihelion on October 29th, just days ago. It swung around the Sun at its closest point, hidden from Earth-based telescopes by the glare of our star, and during that window, during those precious days when nobody could see what was happening, something changed. 3I Atlas began exhibiting non-gravitational acceleration. NASA confirmed it. The Jet Propulsion Laboratory published the data. The object is moving in ways that gravity alone cannot explain, as if it expelled mass, as if it burned fuel, as if it pushed itself along a new trajectory. And if 3I Atlas expelled something, if it jettisoned a piece of itself or released a secondary object during perihelion, where would that object go? It would follow the momentum imparted to it. It would travel along a path determined by the velocity and direction of its release. And if that release happened at the optimal moment, if it occurred during the closest approach to the Sun when orbital mechanics favour such manoeuvres, if it took advantage of what aerospace engineers call the Oberth effect, then the expelled object could achieve a trajectory that takes it precisely where V1 Borisov is right now, directly between 3I Atlas and Earth. This is not fringe speculation confined to conspiracy forums. This theory originated in serious analysis by people who understand orbital dynamics, people who have spent years studying how objects move through space, people who know that when a massive interstellar comet loses enough mass to cause measurable acceleration, that mass has to go somewhere. It does not simply vanish. It follows trajectories, it obeys physics, and if 3I Atlas lost 13% of its mass, as Loeb calculated based on momentum conservation, that is over 5 billion tons of material that should be somewhere, visible, detectable, spreading out in a debris cloud so massive that no telescope on Earth or in orbit could possibly miss it. But we do not see that cloud. Post-perihelion images from November 5th show 3I Atlas as a compact source of light with no clear cometary tail, nothing resembling the expected debris field that should accompany such catastrophic mass loss. The Arnaves Observatory in Spain captured it. The Virtual Telescope project imaged it. Both show the same thing. A fuzzy ball of light, yes, but nothing like the explosive outgassing event that the physics demands. For comparison, on the same day, the same telescope imaged Comet Lemon from our own solar system, and Lemon displays a textbook perfect tail stretching away from the Sun exactly as every comet should. 3I Atlas does not. And now, V1, Borisov sits between it and us, tailless and quiet. Let us dig into the numbers, because numbers do not lie even when people do. V1 Borisov reached perihelion, its closest point to the Sun, on a date calculated as 2025, November 16.53, roughly mid-November. Its perihelion distance measured at 0.46 astronomical units, which places it well inside the orbit of Mercury, deeper in the Sun's gravity well than most comets ever venture. That close to our star, any ordinary icy body should be screaming gas and dust, building a massive coma and tail, glowing brightly as solar radiation blasts material off its surface. V1 Borisov did not do that. Reports describe a nucleus with minimal visible activity. Observers noted a coma and tail only after repeated imaging, and even then the tail remained short, stubby, barely present. For an object at that distance from the Sun, this behaviour is strange. Not impossible, but strange. It suggests either a composition far less volatile than typical comets, or a surface that has been heavily processed, baked, and hardened by previous encounters with stellar radiation, or something else entirely. The orbital elements tell us more. V1 Borisov follows a trajectory with an eccentricity of 1.0096, which means it is hyperbolic, unbound from the Sun's gravity, passing through on a one-time trip just like 3I Atlas. Its inclination measures 112.7 degrees, meaning it moves retrograde relative to the planets, backward compared to the direction everything else in the solar system orbits, and its path brought it within spitting distance of Earth at precisely the moment when 3I Atlas emerged from behind the Sun and became visible again to ground-based telescopes. Coincidence? Maybe. The universe is large and strange things happen. But when you stack coincidence on top of coincidence, when you pile anomaly onto anomaly until the tower of improbabilities reaches the ceiling, you start to wonder if maybe, just maybe, someone or something is stacking the deck. The speculation that V1 Borisov could be a probe deployed by 3I Atlas rests on several pillars of logic, each one shaky when standing alone but reinforced when braced against the others. First, 3I Atlas lost mass. We know this because NASA measured non-gravitational acceleration, and the only way a comet exhibits that acceleration naturally is by expelling gas and dust, by venting material that acts like a rocket engine, pushing the object along a new path. 13% mass loss minimum, Loeb calculated. 5 billion tons. That material has to be somewhere. Second, 3I Atlas displays no visible debris cloud. Post-perihelion images show nothing resembling the expected plume. If the lost mass spread out evenly in all directions, it would create a glow, a diffuse shell of gas and dust that telescopes could not miss. If it vented, preferentially in one direction, it would create a jet, a stream, something. We see neither. The simplest explanation? The mass did not spread out. It remained coherent. It stayed together. It travelled as a single object or a cluster of objects on ballistic trajectories calculated and controlled. Third, V1 Borisov appeared at the right time in the right place with the wrong characteristics. It has a nucleus but almost no tail. It sits between 3I Atlas and Earth. It was discovered only after 3I Atlas completed perihelion, only after the larger object had time to perform whatever manoeuvres it intended while hidden behind the Sun. And Borisov, the astronomer, found it not because of any coordinated search effort, but because he happened to be looking, because he is one of the few people on Earth who still hunts for comets manually, scanning the skies with dedication that borders on obsession. What if he found it because it wanted to be found? What if V1 Borisov is transmitting, reflecting, glowing just brightly enough to be noticed by someone like Gennady Borisov, someone who would report it immediately, someone whose discovery would be taken seriously because of his track record, his history, his credibility? I am not saying this is what happened. I am saying this is what people are asking, and the questions are legitimate even if the answers remain uncertain. Now let us talk about trajectory deviation. When 3I ATLAS entered our solar system, astronomers calculated its path based on gravitational influences alone. The sun's pull, the planet's subtle tugs, the clean mathematics of orbital mechanics. Those calculations predicted where the comet would be at any given time with high precision. But as observations accumulated, as more data poured in from telescopes around the world and instruments in space, discrepancies appeared. Small at first, tiny deviations measured in kilometres across distances of millions of kilometres, barely noticeable, well within the margin of error. But the deviations grew. By October, by the time 3I ATLAS approached perihelion, the difference between predicted and observed positions reached levels that demanded explanation. NASA attributed it to outgassing, a standard answer for comets that drift off course. Gas escaping from the surface acts like tiny rocket thrusters, pushing the comet in directions that gravity alone would not explain. Perfectly normal, perfectly reasonable, except 3I ATLAS is not perfectly normal, and the outgassing explanation requires that missing debris cloud, that 5 billion ton plume of material that nobody can find. If the comet vented enough gas to alter its trajectory measurably, we would see the gas. We would detect it in spectroscopy, in imaging, in the simple visual observations that amateur astronomers conduct every clear night. We see nothing on the scale required, so where did the mass go? If 3I ATLAS expelled 13% of itself, and if that material did not spread into a visible cloud, then it went somewhere specific. It travelled along a specific vector, and if you were designing a mothership, if you were an intelligence from another star system, navigating our solar system for the first time, and if you wanted to deploy a smaller probe for closer observation of the inner planets, perihelion would be the exact moment to do it. The sun's gravity would be at its strongest, the velocities would be at their peak, the Oberth effect would give you maximum efficiency for any manoeuvre. You would release your probe at perihelion, impart the necessary delta V, the change in velocity, and send it along a carefully calculated path that brings it close to Earth, while the mothership continues outward on its original course. V1 Borisov appeared 4 days after 3I ATLAS reached perihelion. It occupies a position between the interstellar visitor and Earth. It displays characteristics inconsistent with normal cometary behaviour at its distance from the Sun, and it will make its closest approach to our planet at 103 million kilometres, close enough to observe, close enough to study, close enough to matter. Does this prove anything? No. Proof requires more than circumstantial alignment. Proof requires direct evidence, spectroscopy showing artificial materials, radio signals carrying information, imagery revealing structures that nature does not build. We have none of that, not yet. What we have is a pattern, a sequence of events that fits together too neatly to dismiss, too strangely to ignore. The internet is alive with speculation. Forums dedicated to 3I ATLAS now dedicate entire threads to V1 Borisov. People share orbital plots, calculate trajectories, overlay paths and vectors, trying to determine if the physics supports the probe hypothesis. Some dismiss it as fantasy, wishful thinking by people who want aliens to be real so badly that they see artificiality in every shadow. Others point to the numbers and ask how many coincidences we are expected to swallow before we acknowledge that maybe this one time, the anomaly is real. Gennady Borisov himself has not commented publicly on the speculation. He reported his discovery through proper channels, submitted his data, and moved on. That is what professional astronomers do. They observe, they report, they let others theorize. But his discovery has already ignited debates that will not fade quickly, questions that will not be satisfied by easy answers or appeals to authority. Because here is the uncomfortable truth. If V1 Borisov is a probe, if it was deployed by 3i ATLAS as an advanced scout or study instrument, then we are not alone, and we are being watched, and the watchers are here right now, positioned between their mothership and our world, observing us with instruments and intentions we cannot begin to guess. And if it is not a probe, if it truly is just another comet, then we have to explain why it appeared exactly where it did, exactly when it did, with exactly the characteristics it displays, at exactly the moment when the most anomalous object in astronomical history completed its closest approach to the Sun. We have to explain that chain of coincidences, and coincidences like that make even skeptics uncomfortable. So what happens next? Observatories around the world continue tracking both objects. 3i ATLAS moves outward now, heading away from the Sun, emerging from the glare that hid it during perihelion, becoming visible again to ground-based telescopes as it approaches its closest point to Earth on December 19th. V1. Borisov follows its own path, hyperbolic and unbound, destined to leave the solar system eventually, but still close enough to watch, to study, to analyse for as long as our instruments can hold it in their sights. The data will accumulate, spectroscopy will reveal composition, light curves will show rotation and activity, trajectory measurements will become more precise, and maybe, in the coming weeks, we will find answers that settle the questions. Maybe we will discover that V1 Borisov is exactly what it appears to be at first glance, a small comet on a lonely journey through the cosmos, unremarkable except for its timing. Or maybe we will find something else, something that does not fit the models, something that forces us to confront possibilities we have spent lifetimes avoiding, questions we have been too afraid or too arrogant to ask seriously. Either way, the sky has changed. Two objects from beyond our solar system occupy our space simultaneously now, and one of them sits directly between the other and Earth, watching, waiting, silent. Welcome to November 7th, 2025. Let us see what the universe has planned for us next. The government blackout. While the world fixates on what appeared between 3i ATLAS and Earth, another story unfolds in the shadows of bureaucracy, and this one stinks of deliberate obstruction. NASA has images of 3i ATLAS that nobody outside a select group of government employees has seen. High-resolution images. The kind of images that could settle every debate raging across the internet right now. Images captured by the Mars Reconnaissance Orbiter using its high-rise camera on October 2nd and 3rd, when the interstellar visitor passed within 29 million kilometres of Mars. That is close. Closer than any spacecraft humanity has ever deliberately sent to photograph an interstellar object. The high-rise camera, with its 50-centimetre aperture, achieved a spatial resolution of 30 kilometres per pixel. For context, that is 3 times better than the best Hubble Space Telescope image taken on July 21st. 3 times better, 3 times sharper, 3 times more detailed. Enough resolution to see surface structures, fragmentation patterns, outgassing jets, anything that might confirm or deny the comet hypothesis, anything that might reveal whether 3i ATLAS is a natural object or something else entirely. NASA has not released those images. It has been over a month, 35 days as of today, November 7th, and counting. The official explanation is simple, clean, bureaucratically airtight. The United States federal government shut down on October 1st. Funding lapsed. Non-essential personnel were furloughed. Data processing pipelines froze. Review processes halted. Public communications ceased. The high-rise images exist somewhere in NASA's servers, but the people authorized to process them, calibrate them, and release them to the public are not working because Congress failed to pass a budget and the government closed its doors. Convenient timing, is it not? 3i ATLAS reaches its closest approach to Mars on October 3rd. NASA captures the best images ever taken of an interstellar object. 2 days earlier, the government shuts down. The images sit locked behind administrative barriers, while the most significant astronomical event in modern history unfolds without the data that could actually tell us what we are looking at. Avi Loeb, the Harvard astrophysicist who has been documenting 3i ATLAS's anomalies since discovery, put it bluntly in a Medium post on November 1st. He wrote, and I am paraphrasing here because I cannot quote directly, that we should not hold science hostage to the shutdown politics of the day. He called the delay a sign not of extraterrestrial intelligence but of terrestrial stupidity. He emphasized that the scientific community would greatly benefit from the dissemination of this time-sensitive data as astronomers plan follow-up observations in the coming months. Time-sensitive. That phrase matters. 3i ATLAS is moving. Every day it travels farther from Mars, farther from the Sun, dimming as it goes. The window for ground-based observations narrows with each passing hour. Coordinating telescope time requires advanced planning. Observers need to know what they are looking for, where to point their instruments, what wavelengths to prioritize. The high-rise images could guide those decisions. Without them, astronomers work blind, guessing at what might be important, wasting precious observation time on redundant measurements while critical data goes uncollected. But NASA stays silent. The images remain unreleased. And the shutdown excuse, while technically accurate, does not explain why other NASA missions continue flowing data without interruption. The James Webb Space Telescope releases images. Hubble maintains its observation schedule. Mars rovers send back photographs. Europa Clipper transmits telemetry. Somehow, the government shutdown affects only the specific data everyone wants to see. Congresswoman Anna Paulina Luna from Florida recognized the problem. On October 31st, she sent a formal letter to Sean Duffy, NASA's acting administrator. The letter requested the immediate release of observational data related to 3i ATLAS, including the high-rise images, as well as additional information on interstellar objects and meteors of scientific interest. She stated explicitly that this information is of great importance to advancing our understanding of interstellar visitors and their interaction with our solar system. Luna did not write that letter casually. She consulted with Loeb beforehand. Joe Rogan suggested on his podcast that Loeb contact NASA's interim administrator directly, and Loeb reached out to Luna instead, understanding that political pressure carries weight that scientific requests do not. Luna responded quickly, professionally, and forcefully. Her letter made clear that the delay is unacceptable, that national security implications exist when unknown objects transit our solar system, that transparency serves the public interest better than bureaucratic stonewalling. On November 5th, Luna posted an update on X, formerly Twitter. She wrote that she had a good conversation with NASA regarding 3i ATLAS, and that the agency will release images and data as soon as the government reopens. Unfortunately, due to bureaucratic reasons, they cannot until then. Unfortunately. Bureaucratic reasons. As if we are discussing routine administrative paperwork and not the most anomalous object ever observed by human instruments. As if the rules matter more than the reality unfolding above our heads. But here is where the story gets interesting in ways that make the shutdown excuse look even thinner. While NASA withholds its high-rise images, citing government paralysis, the European Space Agency has no such constraints. ESA operates independently of American politics. Its missions, including Mars Express and the ExoMars Trace Gas Orbiter, both attempted to photograph 3i ATLAS during its Mars flyby in early October. ESA released images, not many. 2 images out of 488 that they captured. 2 images showing 3i ATLAS as a fuzzy white dot against the black of space. Why only 2 images? ESA has not explained. The ExoMars Trace Gas Orbiter, equipped with cameras designed to study Mars in high resolution, turned those cameras toward 3i ATLAS and captured hundreds of frames. The spacecraft team processed 2. They released 2. The other 486 remain locked away, unexplained, unexamined by anyone outside ESA's internal review process. China acted differently. On November 6th, the China National Space Administration released images captured by the Tianwen-1 Mars orbiter on October 3rd. The images show 3i ATLAS's nucleus surrounded by a coma, with a diameter stretching between 5,000 and 10,000 kilometers. The high-resolution imaging camera aboard Tianwen-1 has a primary mirror diameter of 38.7 centimeters, slightly smaller than high-rise, but still capable of resolving details invisible to Earth-based telescopes. CNSA acknowledged in their statement that photographing such a distant and relatively faint target, 10,000 to 100,000 times darker than surface features on Mars, represented a significant technical challenge. They did it anyway. They released the images. They contributed to the global scientific effort without demanding that international politics defer to bureaucratic convenience. NASA did not. NASA, with the superior high-rise camera, with better resolution and clearer images, maintains its silence. The shutdown excuse wears thinner by the day. Now let us examine what this delay actually prevents. The high-rise images could reveal structural details about 3I Atlas's nucleus. Is it a single solid body or a loose aggregate of fragments barely held together by weak gravity? Does it show signs of artificial geometry, edges and surfaces that nature does not create? Or does it display the irregular potato shape typical of comets and asteroids? Are there jets visible, localized sources of outgassing that would explain the non-gravitational acceleration? Or is the surface uniformly quiet, inactive, inconsistent with the mass loss required to produce measurable trajectory changes? These questions matter. They are not academic exercises for researchers with too much time and too little sense. They are foundational questions about the nature of what is currently moving through our solar system, and the answers exist in data that NASA refuses to release. The images could also reveal the truth about the missing debris cloud. Loeb calculated that 3I Atlas must have lost over 5 billion tons of material to generate the observed non-gravitational acceleration. That mass should be visible as a diffuse shell of gas and dust surrounding the nucleus, glowing faintly as sunlight scatters off the particles. HiRISE, with its superior resolution, could detect that glow if it exists. The absence of such a glow in HiRISE images would constitute the 10th anomaly, a data point so significant that it would force even skeptics to reconsider their comfortable assumptions about what 3I Atlas actually is. NASA knows this. The agency understands what the images show. Someone inside NASA has seen those images, processed them enough to know what they reveal, and decided that the public does not need to see them yet. The shutdown provides cover, plausible deniability, a bureaucratic fig leaf that hides decisions made for reasons that have nothing to do with funding lapses or furloughed employees. Loeb addressed this directly in his writings. He noted that the delay is probably not a sign of extraterrestrial intelligence, but rather of terrestrial stupidity, but that phrasing leaves room for interpretation. Probably not. Probably. The choice of words matters. Loeb is careful with language. He writes precisely, scientifically, choosing each term for accuracy rather than rhetoric. When he says probably, he means that while stupidity is the most likely explanation, other possibilities exist, and those possibilities include deliberate suppression of data that could trigger public panic or institutional embarrassment. What if the high-rise images show something NASA cannot easily explain? What if they reveal structures or behaviours that fall outside the agency's comfortable models of cometary physics? What if they provide evidence supporting Loeb's hypothesis that 3I Atlas might be technological in origin? NASA has already rejected that hypothesis publicly. Tom Statler, the agency's lead scientist for solar system small bodies, told The Guardian that 3I Atlas looks like a comet, does comet things, and very, very strongly resembles in just about every way the comets we know. But Statler has not seen all the data. He bases his statements on incomplete information, filtered through institutional biases that favour natural explanations over uncomfortable alternatives. If the high-rise images contradict his confident dismissal, if they show something that does not look like any comet we know, then releasing those images makes NASA look foolish, reactive, untrustworthy. Better to sit on the data, wait for the news cycle to move on, hope that public interest fades before the truth becomes impossible to hide. That strategy might work for routine discoveries. It fails spectacularly when the object in question is hurtling toward Earth at speeds exceeding 200,000 kilometers per hour and will reach its closest approach on December the 19th, just over a month from now. The public knows something is wrong. You can feel it in the discourse online, in the forums and comment sections and social media threads where people discuss 3I Atlas, with a mixture of fascination and fear. The government blackout feeds conspiracy theories that might otherwise wither from lack of evidence. When officials refuse to release data, when they hide behind procedural excuses that collapse under basic scrutiny, when they treat the public like children too fragile to handle difficult truths, they create the exact conditions that breed distrust and paranoia. Some of that distrust is justified. NASA has a history of controlling narratives, of shaping public perception through selective disclosure, of prioritizing institutional reputation over scientific transparency. The agency serves multiple masters, Congress for funding, the White House for political cover, the scientific community for credibility, the public for legitimacy. Balancing those competing interests requires careful message management, and message management sometimes means withholding information until the right spin can be applied. But 3i ATLAS does not wait for spin. It moves according to physics, following trajectories determined by forces we can measure even if we cannot yet explain them fully. December 19th approaches whether NASA is ready or not, whether the government reopens or not, whether the public receives the data it deserves or remains ignorant of what travels toward us through the dark. Meanwhile, astronomers plan their observations based on incomplete information. The International Asteroid Warning Network announced a coordinated campaign running from November 27th through January 27th, focused on improving astrometry for comet observations. They need accurate position measurements to refine trajectory predictions, to determine whether 3i ATLAS will follow its expected path or deviate again, to check for any unusual activity as it approaches Earth. That campaign would benefit enormously from the high-rise images. Knowing the exact size, shape and activity state of the nucleus helps constrain the models that predict how solar radiation pressure affects the trajectory. Without that data, astronomers work with estimates, assumptions, educated guesses that might be wrong by factors large enough to matter. NASA withholds the images anyway. The shutdown excuse provides cover. The bureaucracy grinds slowly, and the clock ticks toward December 19th, when 3i ATLAS reaches its closest point to Earth and the window for ground-based observations opens wide, assuming anyone bothered to plan properly, assuming the data needed for that planning was ever released, assuming NASA eventually decides that public interest outweighs institutional convenience. Loeb summarized the situation with characteristic directness. We should not hold science hostage to the shutdown politics of the day, but science is held hostage, has been held hostage for 35 days and counting, and will remain hostage until someone with authority decides that transparency matters more than control. Until then, we wait. The images exist. The truth sits on servers inside NASA facilities, backed up and preserved, waiting for the bureaucracy to move, for the government to reopen, for permission to be granted by people who care more about protocols than discoveries. And 3i ATLAS continues its journey, indifferent to our politics, our delays, our carefully managed narratives. It will be here on December 19th, regardless of what NASA chooses to reveal. The only question is whether we will face it informed or ignorant, prepared or blind, understanding what approaches or clinging to comfortable lies that crumble under the weight of data too obvious to deny. No tale, no explanation. On November 5th, 2 observatories released new images of 3i ATLAS, and what those images show, or rather what they do not show, represents a crisis for anyone still clinging to the natural comet hypothesis. The Arnaves Observatory in Bégor, Spain, captured 3i ATLAS post-perihelion using their standard imaging equipment. The Virtual Telescope project in Manciano, Italy, did the same, averaging 2 1200-second exposures taken remotely with their Celestron C14 robotic unit. Both facilities operate, professionally despite their modest size. Both have established track records of reliable comet observations. Both imaged 3i ATLAS under challenging conditions, with an extremely bright moon setting and the target barely 8 degrees above the eastern horizon at nautical twilight. Both show the same thing, a compact source of light. A fuzzy ball with a diffuse glow around it, yes, but no clear cometary tail extending away from the sun. No obvious jet structures, no massive debris plume, nothing that resembles what should be there if 3i ATLAS is behaving like every other comet humanity has ever observed. The images are not ambiguous. They are not blurred or corrupted or suffering from instrumental artifacts that might hide a tail invisible to the camera, but present in reality. The cometary nature of the object is obvious, the diffuse coma unmistakable, but the tail that physics demands simply does not appear. The Arnaves image includes an arrow pointing in the anti-sun direction, showing where the tail should be if 3i ATLAS were following the rules. The space in that direction shows nothing unusual, no brightening, no extension, no structure. For comparison, the Arnaves Observatory also imaged Comet Lemon on November 3rd, just 2 days before capturing 3i ATLAS. Comet Lemon, a perfectly ordinary visitor from our solar system's own reservoir of icy bodies, displays a textbook perfect tail. Clear, bright, unmistakable, pointing exactly away from the sun as solar radiation pressure and the solar wind push gas and dust into the characteristic cometary shape that everyone recognizes. Lemon looks like a comet should look. It follows the rules. It behaves predictably. 3I ATLAS does not, and that is a problem that grows larger the more you think about it. Let us walk through the physics, because the physics do not care about our preferences or our institutional biases or our comfortable assumptions. When a comet approaches the sun, solar radiation heats its surface. Ice sublimates, turning directly from solid to gas without passing through a liquid phase. The gas escapes, carrying dust particles with it, creating the coma and tail that define comets in the popular imagination. The closer the comet gets to the sun, the more intense the heating, the more vigorous the outgassing, the larger and brighter the tail. 3I ATLAS reached perihelion on October 29th at a distance of 203 million kilometres, about 1.4 astronomical units. That is closer than Mars but farther than Earth. It is not an extreme perihelion by cometary standards. Plenty of comets pass much closer to the sun and survive. But it is close enough that significant outgassing should occur, especially for an object that NASA claims exhibited enough activity to generate non-gravitational acceleration. That acceleration tells us how much mass the comet lost. Loeb calculated this based on momentum conservation. When gas escapes from a comet, it carries momentum. That momentum came from the comet itself. The comet must recoil in the opposite direction like a rocket burning fuel. The amount of recoil depends on how much gas escaped and how fast it moved. NASA measured the recoil. From that measurement, we can work backward to determine the mass loss. The answer came to over 13% of the comet's total mass. 13%. For an object estimated to weigh tens of billions of tons, that means over 5 billion tons of material vented into space during the perihelion passage. 5 billion tons of gas and dust should create a cloud so massive, so bright, so obvious, that missing it would be impossible. It should dwarf the nucleus. It should extend for millions of kilometres. It should glow intensely as sunlight scatters off the particles. The November 5th images show nothing like that. The coma visible in those images spans a few thousand kilometres at most, comparable to what Hubble observed back in July when 3I ATLAS was much farther from the Sun and presumably much less active. If the comet vented 5 billion tons of material during perihelion, where did it go? Why is it not visible in every image taken since October 29th? You cannot hide 5 billion tons of gas and dust. You cannot make it invisible. The particles scatter sunlight. They glow. They create a signal that telescopes detect automatically, without special filters or exotic observation techniques. Amateur astronomers with backyard equipment can see cometary tails. They photograph them regularly, posting their images online for the community to admire. Comet Lemon's tail is visible to anyone with a decent telescope and a clear night sky. 3I ATLAS's tail, the tail that should be enormous after losing 13% of its mass, does not appear in professional observatory images taken under controlled conditions by experienced astronomers who know exactly what they are looking for. This is the 10th anomaly. Loeb listed it explicitly in his post on November 5th. Non-gravitational acceleration without the required massive coma. The comet exhibits behaviour that demands outgassing on a catastrophic scale, but the evidence of that outgassing does not exist in the observational data. The effect is present, the cause is absent. That is not how physics works. That is not how anything works, unless 3I ATLAS is not a comet. The alternative explanations are limited and uncomfortable. First possibility, the mass loss did not occur through outgassing. The comet lost mass some other way, through fragmentation perhaps, shedding large chunks of itself that travelled away on ballistic trajectories rather than spreading out as a diffuse cloud. But fragmentation events are dramatic and obvious. They create dust clouds as the broken pieces crumble and collide. Hubble has observed fragmenting comets before. They look chaotic, messy, spectacular. 3I ATLAS looks compact and organised. Second possibility, the outgassing occurred but in a highly directed manner, venting material preferentially in one direction, like a rocket engine, rather than in all directions like a typical comet. Directed outgassing could explain the acceleration without creating a visible tail if the gas jetted away from the Sun, toward the Sun, or perpendicular to the Sun, anywhere except in the anti-Sun direction where tails normally appear. But directed outgassing requires structures, vents, nozzles, mechanisms that concentrate the flow rather than letting it escape randomly through cracks and pores in the surface. Natural comets do not have nozzles. Spacecraft do. Third possibility, the mass loss happened but the material did not spread out. It remained coherent, travelling together as a single object or cluster of objects on trajectories determined by something other than random thermal motion. This brings us back to the probe hypothesis. The idea that 3I ATLAS deployed something during perihelion, released a payload that carried away 13% of the parent body's mass without creating a visible debris field because it was not debris, it was intentional, designed, controlled. None of these explanations sit comfortably within the natural comet framework. Loeb acknowledged this in his writing. He stated clearly that if such a massive cloud is not observed, then the 10th anomaly of 3I ATLAS would be the display of non-gravitational acceleration without the required massive coma. He did not call it proof of artificiality. He called it an anomaly, a data point that does not fit the model, a problem that demands explanation. The scientific community has not provided that explanation. NASA has not addressed the missing tail. The European Space Agency has not commented on the discrepancy between predicted and observed post-perihelion behaviour. The silence from official channels is deafening, and in that silence, speculation flourishes. Some researchers point to the blue colour that 3I ATLAS reportedly developed during perihelion. Blue is unusual for comets. Dust reflects sunlight in reddish tones. Gas emission lines can produce various colours depending on composition, but most cometary gas glows green from excited carbon molecules or red from ionised oxygen. Blue suggests something different, possibly ionised carbon monoxide, possibly emission from heated metal surfaces, possibly artificial light sources. Loeb raised this possibility in his analysis. He noted that the blue colour could potentially be explained by a hot engine or a source of artificial light, though he added that it might instead be a signature of ionised carbon monoxide for a natural comet. The phrasing is careful, balanced, acknowledging uncertainty while refusing to dismiss possibilities that lack definitive evidence against them. But the blue colour is secondary to the missing tail. Colour can be debated. Spectral lines can be reinterpreted. Instrumental calibrations can be questioned. A missing tail when physics demands a present tail is harder to explain away. Either the physics is wrong, which seems unlikely given that we have observed hundreds of comets, and they all behave consistently, or 3I ATLAS is not following the physics because it is not what we think it is. The Virtual Telescope Project image from November 5th was taken under particularly challenging conditions. An almost full moon washed out the sky. The target sat low on the horizon where atmospheric extinction dims everything. Despite those obstacles, the diffuse cometary nature of 3I ATLAS came through clearly in the data. But the tail did not. The coma, yes. The tail, no. That distinction matters. Coma forms when gas escapes the nucleus and surrounds it with a glowing shell. Coma is local, bound loosely to the nucleus by weak gravity and the low velocities of the escaping gas. Tail forms when solar radiation pressure and the solar wind push that gas away from the nucleus at high speed, stretching it into the elongated structure that can extend for millions of kilometres. Coma without tail suggests low activity, minimal outgassing, a comet that is barely active despite its proximity to the Sun, but 3I ATLAS is not barely active. NASA's data proves it. The non-gravitational acceleration requires significant activity, massive outgassing, the kind of gas production that builds tails you can see from Earth without advanced equipment. The contradiction is stark and unresolved. Some skeptics argue that the tail might be present but oriented in a way that makes it difficult to observe from Earth's perspective. Geometric effects can hide tails temporarily, angling them edge-on or foreshortening them so they appear shorter than they actually are. But 3I ATLAS passed perihelion over a week before these November 5th images. It moved far enough from solar conjunction that Earth-based telescopes had clear views. The geometry was favourable for tail detection. If the tail existed, the November 5th observations should have caught it. They did not. And on the same day, the same telescopes imaged Comet Lemon with a glorious tail that looked exactly as expected, proving that the instruments worked, the conditions allowed for tail detection, and the observers knew what they were doing. The problem is not with the observations, the problem is with the object. Loeb compiled the list of anomalies systematically, documenting each one with references to published data and peer-reviewed analysis. The missing tail, if confirmed by continued observations, joins retrograde trajectory alignment, sunward jets, unusual mass and velocity, fine-tuned arrival timing, extreme nickel emissions, alignment with historical radio signals, self-luminosity questions, and rapid brightening events. Each anomaly stands on its own as something strange, something worth investigating, something that pushes the boundaries of what we expect from natural objects. Together they form a pattern. Patterns suggest design. Design suggests intelligence. Intelligence suggests that 3I ATLAS might be exactly what Loeb cautiously proposed from the beginning, a technological artifact from another civilization, travelling through our solar system on a mission we do not understand, exhibiting behaviours that make sense only if we abandon the comfortable assumption that everything in space is natural. The missing tail is not proof, but it is evidence, it is data, it is a fact that demands explanation. And so far, the explanations offered by those who insist 3I ATLAS is a normal comet have been inadequate, incomplete, unsatisfying. On December 19th, 3I ATLAS will pass Earth at its closest approach. Ground-based observatories will have their best opportunity to observe the object in detail, to measure its activity, to search for that elusive tail that should be there if the physics is right. If the tail remains absent, if 3I ATLAS continues displaying non-gravitational acceleration without the corresponding debris cloud, then the 10th anomaly becomes impossible to ignore, and if we cannot ignore it, we have to explain it. The explanations available are few, and most of them lead to conclusions that make institutional astronomers very uncomfortable. But discomfort is not a scientific argument. The data is what it is. The tail is missing. And missing tails on active comets do not happen in nature. Not on the scale 3I ATLAS requires. Not with the consistency the observations show. Something is wrong. The images from November 5th prove it. What remains to be seen is whether anyone with authority will acknowledge what the data is screaming at us, or whether we will continue pretending that everything is normal, while the universe shows us very clearly that normal ended the day 3I ATLAS entered our solar system. The blue transformation colour means something in astronomy. It is not decorative or subjective or open to interpretation. Colour tells us about temperature, composition, chemical processes, energy sources. When an object's colour changes, physics demands an explanation. When that object is an interstellar visitor exhibiting unprecedented behaviour, and when its colour shifts to something comets do not normally display, the explanation becomes urgent. 3I ATLAS turned blue, not metaphorically, not in artistic renderings or false colour composites designed to highlight certain wavelengths. The object developed a distinctly blue hue, observable in photometric data collected by spacecraft monitoring its perihelion passage. Blue light, shorter wavelengths, higher energy photons than the reddish or neutral tones typical of cometary dust and gas. This is the third time observers have noted a colour change since discovery in July. 3 times. 3 distinct shifts in the spectral signature of an object that should remain relatively constant in colour unless something dramatic happens to its composition or activity state. Normal comets do change colour slightly as they approach the Sun, as different ices sublimate at different temperatures, as dust production varies with solar heating. But those changes are subtle, gradual, predictable. 3I ATLAS's colour shifts are none of those things. The blue colour appeared during or immediately after perihelion, when the comet was hidden behind the Sun from Earth perspective but visible to certain spacecraft positioned favourably in the inner solar system. Researchers analysing data from those spacecraft noted the colour shift in a preprint paper, discussing the rapid brightening event that accompanied perihelion passage. They described 3I ATLAS as distinctly bluer than the Sun, a comparison that matters because sunlight reflected off cometary dust typically matches or slightly exceeds solar colour temperature, leaning toward reds and oranges as larger dust particles scatter longer wavelengths preferentially. Blue means something different is happening. Blue means shorter wavelengths dominate. Blue means higher energy processes, hotter surfaces, or emission mechanisms that do not rely on simple reflection of sunlight. Loeb addressed this in his analysis. He noted that for a natural comet, this blue colour is very surprising. Dust would result in having a redder colour than the Sun. The observation contradicts basic physics of light scattering. Small particles scatter blue light more efficiently than red, which is why Earth's sky appears blue. But cometary dust particles are typically large enough that this effect becomes weak or reverses, making comets appear reddish rather than bluish. So what produces blue light from 3I ATLAS? Loeb offered two categories of explanation. First, natural processes. Ionized carbon monoxide emits blue light. Carbon monoxide, chemical formula CO, is a common cometary gas. When intense ultraviolet radiation from the Sun strips electrons from CO molecules, the resulting ions glow blue as electrons recombine and cascade down through energy levels. If 3I ATLAS vented massive amounts of carbon monoxide during perihelion, and if that gas became highly ionized in the intense solar radiation environment close to the Sun, the resulting glow could appear blue. This explanation works. It is plausible. It invokes nothing exotic, nothing beyond established chemistry and atomic physics. Ionized carbon monoxide is a known quantity. We have observed it in other astronomical contexts. Attributing the blue colour to ionized CO requires no speculation, no appeal to unusual mechanisms, no departure from consensus science. But it requires massive outgassing. Enough carbon monoxide to produce a visible blue glow must be released in quantities large enough to dominate the spectral signature of the entire coma. That much gas creates a debris cloud, a big one. The kind we already established is missing from the November 5th images. If 3I ATLAS vented enough carbon monoxide to turn blue from ionization, where is the gas now? Why do we not see it spreading out, glowing, creating the tail that should accompany such vigorous activity? The second category of explanation is less comfortable. Loeb wrote that the blue colour could potentially be explained by a hot engine or a source of artificial light. Hot engine, artificial light. These phrases carry implications that institutional astronomy rejects reflexively, but the physics does not care about institutional preferences. If 3I ATLAS contains an engine, if it operates machinery that generates heat, if it uses power sources that emit light in blue wavelengths, then the observed colour makes perfect sense. Engines glow blue. Rocket exhausts burn blue when the combustion temperature is high enough. Ion drives emit blue light as charged particles accelerate through electromagnetic fields. Nuclear reactors produce Cherenkov radiation, that characteristic blue glow visible in water surrounding reactor cores. Any sufficiently advanced propulsion system operating at high power output could produce blue light as a byproduct of its operation. Artificial light sources also tend toward blue. LEDs emit narrow spectral lines. Certain plasma discharges glow blue. Arc welding creates intense blue-white light. If 3I ATLAS carries instruments that use light for communication, sensing, or energy transmission, and if those instruments operated during perihelion, they could produce blue emissions detectable by spacecraft monitoring the comet from a distance. These explanations are speculative. They require accepting that 3I ATLAS might be technological. But speculation based on observational data is how science advances. Dismissing speculation because it makes us uncomfortable is how science stagnates. The timing of the blue colour shift matters. It appeared during perihelion, when 3I ATLAS was at its closest point to the Sun, when solar radiation was most intense, when any onboard systems requiring solar power would have maximum energy available. If the comet is technological, if it carries solar panels or solar thermal collectors or any mechanism for harvesting stellar energy, perihelion is when those systems would operate at peak efficiency. It is also when an engine burn would be most effective. The Oberth effect, named after the German physicist who described it, states that propulsive manoeuvres are most efficient at the point of highest velocity in an orbit. For an object passing through the inner solar system, that point is perihelion. Burning fuel there, accelerating or decelerating at that moment, provides maximum change in kinetic energy for a given expenditure of propellant. If 3I ATLAS performed an engine burn during perihelion, the blue glow could be exhaust. The non-gravitational acceleration could be thrust. The missing debris cloud makes sense because the expelled mass was not random outgassing but directed propulsion. All the pieces fit together if you accept the technological hypothesis. None of the pieces fit cleanly if you insist on natural processes. The rapid brightening that accompanied the colour shift adds another layer to the mystery. 3I ATLAS brightened by a factor of approximately 5 in the green band, centered at a wavelength of 0.464 micrometers. Factor of 5, that is significant. Comets brighten as they approach the Sun, yes, but the increase should be smooth and predictable, based on distance and solar flux. A sudden jump by a factor of 5 suggests something changed abruptly. Something activated or intensified or began operating at a different level. What changes abruptly on a natural comet? Ice can suddenly crack, exposing fresh material to sunlight, but fresh ice is brighter initially and fades as it becomes covered with dust. It does not maintain increased brightness after the initial exposure. Impacts can brighten comets temporarily if another object strikes the nucleus and throws up a plume of fresh material, but 3I ATLAS is in interstellar space, far from the dense populations of asteroids that make collisions likely. The probability of a random impact during the narrow window of perihelion is vanishingly small. Artificial systems change state abruptly all the time. Power systems turn on, instruments activate, engines ignite. Lights switch from standby to operational mode. If 3I ATLAS is a spacecraft, a sudden brightening during perihelion is exactly what you would expect as onboard systems power up, to take advantage of available solar energy, or to perform maneuvers optimized for that location. The color data is not ambiguous. It exists in calibrated photometric measurements collected by professional instruments operated by experienced researchers. The blue shift is real. The question is what causes it, and the answers divide cleanly into two camps. Natural processes that strain credibility and leave multiple observations unexplained, or technological processes that explain everything but require accepting a conclusion that most astronomers find too radical to consider seriously. Loeb does not insist on the technological explanation. He presents it as a possibility, one hypothesis among several, supported by data but not proven by it. His approach is methodical and cautious, acknowledging uncertainty while refusing to dismiss uncomfortable ideas simply because they challenge conventional thinking. This is how science should work. This is how progress happens, by entertaining possibilities that seem unlikely until evidence forces us to reconsider. But institutional science does not work that way. Institutions have reputations to protect, funding to secure, political relationships to maintain. Suggesting that an interstellar object might be artificial invites ridicule from colleagues, skepticism from funding agencies, dismissive coverage from media outlets more interested in reassuring the public than investigating uncomfortable truths. Loeb has faced exactly that response. Critics accuse him of attention-seeking, of lowering scientific standards, of damaging astronomy's credibility by promoting fringe ideas. Yet the data remains. 3I ATLAS turned blue. It brightened rapidly. The colour persisted in observations taken after perihelion. These are facts, not speculation. The speculation comes in the interpretation, in the effort to explain what the facts mean. And so far the natural explanations do not account for the full picture. Consider what we know. The comet exhibits non-gravitational acceleration requiring massive outgassing. The expected debris cloud is absent. The colour shifted to blue during perihelion. The brightening occurred suddenly rather than gradually. The post-perihelion images show a compact object without the extended tail that physics demands. Each of these observations stands alone as an anomaly worth investigating. Together, they form a pattern that natural comet behaviour does not explain. Pattern recognition is a fundamental skill in science. We look for patterns in data because patterns reveal underlying principles, mechanisms, relationships that are not obvious from individual measurements. The pattern emerging from 3I ATLAS observations suggests behaviour inconsistent with natural cometary processes and consistent with technological control. That does not prove artificiality. Proof requires more direct evidence, spectroscopic signatures of industrial materials, radio emissions carrying information, resolved imaging showing geometric structures. We have none of that yet. The high-rise images might provide it, if NASA ever releases them. Ground-based observations on December 19th might add crucial data. Future measurements could confirm or refute the technological hypothesis. But the blue colour stands now as another piece of the puzzle, another data point that does not fit comfortably into the natural framework. Another reason to question whether the assumptions we bring to 3i ATLAS are adequate to explain what we observe. The universe is not obligated to make sense to us. It operates according to physical laws that do not care about our intuitions or our institutional comfort. If 3i ATLAS is artificial, if it represents technology from another civilization, then our inability to accept that possibility says more about our limitations than about the reality of the object itself. Blue light, third colour change, rapid brightening, missing tail, non-gravitational acceleration. The anomalies pile up, each one adding weight to the argument that something deeply unusual is happening, that 3i ATLAS is not playing by the rules we thought governed cometary behaviour. December 19th is coming. The observations planned for that date will either strengthen the natural hypothesis by providing missing pieces that make everything fit together, or they will deepen the mystery by confirming that 3i ATLAS truly is unlike anything we have encountered before. Either way, the blue transformation remains. The data exists. The explanations struggle to account for it without invoking processes that challenge our understanding of what travels through interstellar space, and what it might be capable of doing when it visits our little corner of the galaxy. Think about that for a moment. An object from another star system, older than our own sun, travelling through the void for billions of years, arrives here and turns blue at precisely the moment when it passes closest to our sun. Coincidence? Natural process? Or something else? Something intentional? Something that suggests intelligence and purpose behind the trajectory we track and the light we measure? The answer waits in data we have not yet collected, in images we have not yet seen, in measurements that will be made in the coming weeks as 3i ATLAS approaches Earth, and instruments turn toward it with renewed intensity. But the question is already here, impossible to ignore, growing louder with each new observation that refuses to fit the comfortable narrative. Why is 3i ATLAS blue? And what does that colour tell us about what it really is? Non-gravitational acceleration. Confirmed NASA published the numbers, and the numbers do not lie. 3i ATLAS is accelerating in ways that gravity alone cannot explain. The detection stands at 3.7 standard deviations above background noise, which in the language of physics means this is real, not speculation, not instrumental error, not a statistical fluke that will disappear with more data. Real acceleration, measured repeatedly, confirmed by independent analysis, documented in official reports from the Jet Propulsion Laboratory and the Minor Planet Center. Standard deviations matter in science because they quantify certainty. 1 standard deviation means the signal could easily be noise. 2 standard deviations get interesting but remain questionable. 3 standard deviations start to look convincing. 3.7 standard deviations crosses the threshold where skepticism requires more effort than acceptance. Something is pushing 3i ATLAS off its predicted trajectory, and that something is not the sun's gravity or the gravitational pull of the planets, or any other purely gravitational force we can model. The measurement itself is straightforward. Astronomers observed 3i ATLAS repeatedly over several months, recording its position against background stars with high precision. They calculated where the comet should be based on gravitational forces alone, using models refined over centuries of celestial mechanics. Then they compared predictions to observations. The object was not where it should be. The deviation grew over time, accumulating as the comet moved through the inner solar system, becoming large enough that attributing it to measurement error became impossible. This is non-gravitational acceleration. The term is standard in cometary astronomy. Comets exhibit it routinely because they are not passive objects. They outgas. They vent material. The escaping gas acts like a rocket engine, pushing the nucleus in directions that pure gravity would not predict. Measuring this acceleration tells us how active the comet is, how much mass it is losing, how the outgassing affects its trajectory. For 3i ATLAS, the acceleration tells us something extraordinary. NASA reported the value normalized to a heliocentric distance of 1 astronomical unit, which is the standard way of expressing non-gravitational acceleration for comparison between different objects at different distances from the Sun. The reported value is significant, large enough to require substantial mass loss, large enough to produce effects visible in trajectory predictions weeks or months in advance. Loeb calculated what this acceleration means in terms of mass loss. He started with momentum conservation, one of the fundamental principles of physics. When gas escapes from a comet, it carries momentum. Momentum cannot be created or destroyed, only transferred. If the gas carries momentum in one direction, the comet must recoil in the opposite direction with equal momentum. By measuring the recoil, which is the non-gravitational acceleration, and knowing roughly how fast the gas escapes, which depends on temperature and molecular weight, we can calculate how much gas was released. The answer shocked even researchers prepared for large numbers. 3I ATLAS must have lost more than 13% of its total mass during the perihelion passage. 13%, not 1%, not 0.1%. 13%, a fraction so large that it represents catastrophic mass loss. The kind of outgassing event that transforms comets fundamentally, that leaves them visibly different, that creates debris clouds so vast they dominate the inner solar system for weeks or months afterward. 5 billion tons. That is the mass equivalent of 13% of 3I ATLAS, assuming the size estimates from Hubble and other observations are correct. 5 billion tons of gas and dust vented into space in a matter of days or weeks, as the comet swung around the Sun. For context, 5 billion tons is roughly the mass of a small asteroid, a mountain of material, enough to fill volumes measured in cubic kilometres. That much material does not disappear. It spreads out, it reflects sunlight. It scatters and glows and creates signatures detectable by every instrument capable of observing the region. It forms a coma, a tail, a structure so obvious that missing it would require deliberately not looking. Yet we have established that the expected coma and tail are not visible in post-perihelion observations. The November 5th images show a compact object. China's Tianwen-1 images show a coma with a diameter of a few thousand kilometres, substantial but nowhere near the scale required if 5 billion tons of material spread out from the nucleus. The debris cloud that should accompany 13% mass loss simply is not there. This is the paradox that drives the entire mystery. The acceleration is real. The mass loss calculation is solid, based on well-established physics. But the consequences of that mass loss are absent from the observational data. Something is deeply wrong with the picture, and the wrongness grows more obvious the more carefully you examine the details. One possibility is that the mass loss did not spread out evenly. Perhaps it vented preferentially in one direction, creating a jet rather than a spherical cloud. Directed outgassing can occur naturally when sublimation happens faster on one side of the nucleus than the other, perhaps because that side faces the Sun more directly, or because the composition varies across the surface. But directed jets are visible. They show up as streamers, plumes, localized bright spots in the coma. Spacecraft have imaged jets on solar system comets in exquisite detail. They are beautiful, dynamic, unmistakable. 3I ATLAS does not display obvious jets in the available imagery. The Hubble image from July showed a teardrop-shaped dust cocoon, which could be interpreted as a weak jet or simply as the natural asymmetry of dust production. Post-perihelion images show a more symmetrical coma with no clear jet structures. If the 5 billion tons vented as a jet, where is it now? Why does it not appear in observations taken from multiple angles by multiple instruments over multiple days? Another possibility is that the outgassing occurred very rapidly, in a brief intense burst rather than a prolonged steady release. Outburst events happen on comets. Sudden crack formations, subsurface ice pockets reaching critical temperature, structural collapses, all these can produce short-lived spikes in activity that then fade quickly. If 3I ATLAS experienced an outburst during perihelion, the resulting debris cloud might have been denser and more compact initially, but spread out and dimmed by the time observers could see the comet after it emerged from solar conjunction. But outbursts leave signatures. They create dust trails, linear features stretched along the comet's orbit marking where the burst occurred and how the material dispersed over time. Solar system comets that experience outbursts are studied intensively afterward, with observers tracking how the ejected material evolves. No one has reported outburst signatures from 3I ATLAS. The object looks quiet, orderly, inconsistent with the chaotic aftermath of a violent mass loss event. The third possibility, the one that explains all the observations simultaneously, is that the expelled mass did not behave like typical cometary debris. It remained coherent. It travelled together as a unit or as a small number of discrete objects. It followed a trajectory determined by something other than random thermal velocities and solar radiation pressure. In short, it was released intentionally, directed, controlled. This brings us back to the technological hypothesis. If 3I ATLAS is artificial, if it operates propulsion systems rather than relying on passive outgassing, then the non-gravitational acceleration is thrust. The expelled mass is propellant. The absence of a visible debris cloud makes sense because rocket exhaust does not hang around glowing for weeks. It disperses quickly, becoming too diffuse and faint to detect within days of the burn. Alternatively, if the expelled mass was a deployed object, a probe or module released from the parent craft, it would travel on its own trajectory without creating a glowing cloud. The mass loss would still register in the non-gravitational acceleration measurements, but the visual signature would be a small compact object rather than a sprawling debris field, and if that object happened to be positioned between 3I ATLAS and Earth, we would know it by a different name. V1 Borisov, perhaps. The Olbers effect keeps appearing in these discussions because it is crucial to understanding optimal manoeuvring in orbital mechanics. When you want to change your trajectory efficiently, you do it at perihelion. When you want to release a probe that will have maximum flexibility in reaching different destinations within a solar system, you release it at perihelion. The timing is not coincidental. It is optimal. It is what any intelligent designer would choose. 3I ATLAS reached perihelion on October 29th. The non-gravitational acceleration spiked during that period. The mass loss that acceleration implies occurred during the days surrounding perihelion, and 4 days later, observers discovered V1 Borisov sitting between 3I ATLAS and Earth, with characteristics that do not match typical cometary behaviour. Pattern or coincidence? The universe contains both. Distinguishing them requires careful analysis, multiple independent lines of evidence, rigorous testing of alternative hypotheses. But patterns become more convincing when they involve multiple correlated events occurring in narrow time windows with low prior probability. 3I ATLAS's perihelion, its mass loss, the timing of V1 Borisov's discovery, the geometry of the two objects relative to Earth, all these factors compound. The probability of everything happening by chance shrinks with each additional constraint you apply. NASA has not offered an alternative explanation. The agency confirmed the non-gravitational acceleration. It published the numbers. It acknowledged that something caused the trajectory to deviate from gravitational predictions. But it has not explained where the 5 billion tons of expelled material went, why the debris cloud is missing, how a comet can lose 13% of its mass without creating visible consequences. Tom Statler's assurance that 3I ATLAS looks like a comet and does comet. Things rings hollow when the comet does not produce the tail that comet things require. The acceleration is measured, the mass loss is calculated, the debris cloud is absent. These three facts form a triangle, and the only way out is to question one of the vertices. Either the acceleration measurement is wrong, which seems unlikely given the statistical significance and independent confirmation, or the mass loss calculation is wrong, which would require abandoning momentum conservation, a pillar of physics. Or the debris cloud is not missing but is somehow invisible, which makes no sense given how light scattering works. Or 3I ATLAS is not a comet, and the entire framework we use to interpret its behaviour is inappropriate. Loeb has been saying this for months, not insisting, not declaring it as fact, but suggesting that the possibility deserves serious consideration, that dismissing it reflexively is bad science, that we should let the data guide our conclusions rather than forcing the data to fit our preferred models. The non-gravitational acceleration is data. It points clearly at massive mass loss. The absence of the corresponding debris cloud is also data. It contradicts the mass loss interpretation if 3I ATLAS is a natural comet. The contradiction resolves if we change the interpretation. If the acceleration comes from propulsion rather than outgassing, if the expelled mass was propellant or deployed hardware rather than random ice and dust, then everything fits. The measurements make sense. The observations align. The paradox disappears. But accepting that resolution requires accepting that we are not alone, that other civilizations exist, that they build spacecraft capable of crossing interstellar space, that one such spacecraft is currently in our solar system performing maneuvers we can detect but not yet fully understand. That is a large step. It is a step many scientists are unwilling to take without overwhelming evidence. What constitutes overwhelming evidence? direct imaging of artificial structures, radio transmissions, close-up photographs from a spacecraft we send to intercept. All those would be convincing, but we may not have time to obtain them before 3I Atlas leaves the solar system forever. The window for investigation is narrow. The object moves fast. December 19th represents our closest approach, our best chance to gather decisive data. If we wait for absolute proof, we might miss the opportunity to investigate while investigation is still possible. If we act on incomplete evidence, we might waste resources chasing a false lead. The balance is delicate and the stakes are enormous. The non-gravitational acceleration is confirmed. 3.7 standard deviations. Real, measured, undeniable. What it means remains open to interpretation, but the range of interpretations has narrowed considerably. Natural processes struggle to explain the observations. Technological processes explain them easily. That does not make the technological hypothesis correct. It makes it competitive. It makes it worthy of serious investigation rather than dismissive rejection. And it makes the data from December 19th absolutely critical to resolving the question one way or another. The numbers do not lie. 3I Atlas is accelerating. Something pushed it off course. Understanding what that something is and how it works defines the difference between a remarkable natural phenomenon and first contact with technology from beyond our world. The December 19th convergence. Mark your calendar. December 19th, 2025. That is the date 3I Atlas reaches its closest point to Earth, passing within 168 million miles, roughly 1.8 astronomical units from our planet. Not close by astronomical standards, no danger of impact, no threat to Earth, but close enough that ground-based telescopes will have their best views, their clearest data, their final opportunity to answer the questions that have haunted this object since discovery. 1.8 astronomical units. Let that sink in for context. The Sun sits 1 astronomical unit from Earth by definition. Mars at closest approach gets within about 0.4 astronomical units. The Moon orbits at 0.00257 astronomical units. 3I Atlas will be farther than Mars, roughly twice the Earth-Sun distance, but that is still remarkably close for an interstellar visitor, travelling at over 200,000 kilometers per hour on a hyperbolic trajectory that will eventually take it out of the solar system forever. This is not a second-chance event. 3I Atlas will not return. Its orbit is unbound, hyperbolic, meaning it has enough velocity to escape the Sun's gravitational pull permanently. It came from interstellar space. It is passing through our solar system once, and it will leave, continuing its journey through the galaxy along a path determined by the forces acting on it during this brief visit. Whatever observations we fail to make on December 19th, we will never have another opportunity to make them. The International Asteroid Warning Network understands this. On November 27th, IAN launches a coordinated observation campaign focused specifically on 3I Atlas, running through January 27th, 2026. 2 months of intensive monitoring, with dozens of observatories around the world contributing data, pooling resources, sharing information in real time to build the most comprehensive picture possible of what this object is and how it behaves. The campaign focuses on astrometry, precise measurements of position over time. Astrometry might sound mundane, but it is foundational. Knowing exactly where 3I Atlas is at any given moment and how that position changes allows astronomers to refine trajectory predictions, to detect any additional non-gravitational accelerations, to determine whether the forces acting on the object remain constant or change as it moves through different regions of space. If 3I Atlas is natural, a typical comet despite its interstellar origin, then its behaviour should become more predictable as we gather more data. Cometary activity depends primarily on distance from the Sun. As the comet moves away from perihelion, it should dim, its outgassing should decrease, its trajectory should stabilise. The astrometry campaign will test these predictions. If the data confirms them, the natural hypothesis gains support. If the data shows continued anomalies, unexpected accelerations, behaviours that do not correlate with solar distance, then the natural hypothesis weakens and alternatives become more compelling. Avi Loeb has been planning for December 19th since October. He tasked the research team of the Galileo Project observatories to watch for any unusual activity of extraterrestrial technological objects near Earth in the coming months. That phrasing is careful and specific. Not watching 3i ATLAS directly, though obviously they will, but watching for unusual activity near Earth. This includes potential probe deployments, trajectory changes, secondary objects released from the primary body, anything that might indicate 3i ATLAS is not travelling alone, or is not simply coasting passively through space. The Galileo project operates multiple observatories equipped with instruments designed specifically to detect and characterise anomalous aerial phenomena, objects in Earth's atmosphere or near space that exhibit behaviours inconsistent with known natural or human-made systems. Applying those instruments to 3i ATLAS represents a strategic choice. If the interstellar visitor is technological, if it deploys probes or monitoring equipment as it approaches Earth, the Galileo project instruments might be the first to notice. Loeb also noted the Oberth effect in the context of December 19th. While perihelion represents the optimal point for major manoeuvres, closest approach to Earth represents an optimal point for a different kind of manoeuvre, a trajectory adjustment aimed at positioning probes or modules in specific orbits around our planet. If 3i ATLAS is a mothership, if it released smaller craft during perihelion, those craft might perform their own manoeuvres as they reach Earth, using our planet's gravity for assists or adjustments that would be difficult or impossible to achieve through propulsion alone. This is not wild speculation. This is orbital mechanics. This is how spacecraft designers think, how mission planners optimize trajectories, how you maximize flexibility and minimize fuel expenditure when navigating between multiple destinations. If an intelligence-designed 3i ATLAS's trajectory, it would take advantage of gravitational assists. It would position deployments at optimal points. It would coordinate arrival times to maximize observational opportunities. December 19th sits 6 weeks after perihelion. 6 weeks for any deployed objects to travel from 3i ATLAS's position at perihelion to positions near Earth. 6 weeks is a plausible transit time for objects moving at velocities consistent with solar system escape, particularly if those objects receive velocity boosts from the perihelion manoeuvre. The geometry works, the timing fits, the hypothesis is testable, and that is what makes December 19th so crucial. We will either observe normal cometary behaviour, a quiet icy body gradually fading as it recedes from the Sun, or we will observe something else, something that demands explanations more complex than outgassing and dust reflection. The data collected during the Iowan campaign will force the conversation forward, will make it impossible to ignore the anomalies by providing such high-quality observations that ambiguity disappears. Multiple spacecraft will also observe 3i ATLAS around this time, though some of their data will not be available immediately. ESA's Jupiter Icy Moons Explorer, known as JUICE, attempted observations in early November, despite the comet being farther from the spacecraft than during the Mars flyby. JUICE carries multiple instruments capable of spectroscopy, imaging, and composition analysis. But the spacecraft is sending data back to Earth slowly, prioritizing its primary mission objectives. We may not see JUICE's 3i ATLAS observations until February 2026, months after the December convergence, too late to inform real-time decision-making but valuable for retrospective analysis. NASA assets remain in play despite the government shutdown complications. Hubble can observe 3i ATLAS again as it emerges fully from solar glare. James Webb Space Telescope has 3i ATLAS on its observation schedule, with near-infrared spectroscopy planned to characterize the coma composition in detail. TESS, the Transiting Exoplanet Survey Satellite, might capture the comet in its wide-field monitoring, providing long-duration photometry that could reveal rotation periods, outburst events, or other time-variable behaviors. Ground-based observatories have the advantage of flexibility. Space telescopes operate on fixed schedules, with observation time allocated months in advance through competitive proposal processes. Ground-based telescopes can react quickly, redirecting to targets of opportunity, following up on unexpected discoveries, coordinating with other observatories to build multi-wavelength datasets in real time. For an object as dynamic and unpredictable as 3i ATLAS, this flexibility is invaluable. Amateur astronomers will also contribute. The community of serious amateur observers has grown enormously in recent decades, with access to telescopes and cameras rivaling professional equipment from a generation ago. Amateurs discovered 3i ATLAS in the first place, or rather the ATLAS Survey Telescope, which operates somewhat between professional and amateur depending on how you define the terms. Backyard observers with 30cm aperture telescopes can detect 3i ATLAS, can measure its brightness, can track its position, can contribute data points to the astrometry campaign. Loeb mentioned specifically that any telescope with an aperture larger than 30cm can observe 3i ATLAS on December 19th. 30cm is a 12-inch diameter mirror, a size common among serious amateur astronomers, not requiring university funding or government grants, accessible to dedicated individuals with passion and persistence. This democratization of observation means that thousands of eyes will turn toward 3i ATLAS, thousands of data streams will feed into the collective effort to understand what we are seeing. What should we look for? What observations would be decisive, tipping the scales toward natural or artificial interpretations? Several targets stand out as high priority. First, spectroscopy. Detailed spectral analysis can identify specific molecules in the coma, their relative abundances, their ionization states, their spatial distribution around the nucleus. If 3i ATLAS is natural, its spectrum should match other comets, showing water, carbon dioxide, carbon monoxide, methane, ammonia, the usual mix of volatiles we associate with icy bodies. If the spectrum shows unusual abundances, if nickel dominates without corresponding iron as earlier observations suggested, if industrial alloys or exotic compounds appear that have no business in a pristine comet from the outer reaches of another star system, then the natural hypothesis takes a serious hit. Second, imaging resolution. While HiRISE captured the best images during the Mars flyby, ground-based observatories using adaptive optics can achieve impressive resolution, particularly for bright objects. Adaptive optic systems compensate for atmospheric turbulence, sharpening images to approach the theoretical limit imposed by the telescope's aperture. The Very Large Telescope, Keck Observatory, Gemini, all have adaptive optics capabilities. Applied to 3i ATLAS on December 19th, these systems might resolve surface features, detect rotation through brightness variations, identify jets or active regions, distinguish between a monolithic nucleus and a rubble pile aggregate. Third, polarimetry. The polarization of reflected sunlight depends on particle size, composition, and surface texture. Cometary dust typically produces characteristic polarization signatures that we understand well from decades of solar system comet observations. If 3i ATLAS produces different polarization, if the signature matches metallic surfaces or geometric structures rather, then irregular dust grains that would constitute strong evidence for artificiality. Fourth, variability. Does 3i ATLAS change brightness periodically, suggesting rotation? Does it brighten or dim erratically, suggesting outburst events or attitude adjustments? Does it exhibit periodic signatures in any wavelength band that might indicate active systems cycling on and off? Continuous monitoring over days or weeks can reveal these patterns, building a time series that characterizes how the object behaves over intervals longer than a single observation. Fifth, secondary objects. Are there small bodies near 3i ATLAS travelling with it, orbiting around it, deployed from it? Surveys with wide-field cameras can search the region around the primary object for fainter companions. Finding such objects would not prove they were deployed artificially, but their orbital characteristics could be revealing. Natural fragments from a comet breakup follow predictable trajectories determined by the velocity and timing of the fragmentation event. Artificial deployments can have much more varied trajectories, optimized for specific destinations rather than constrained by the physics of passive fragmentation. The Galileo project's mandate includes searching for exactly these kinds of secondary objects. Loeb's emphasis on watching for unusual activity near Earth reflects awareness that the convergence date might not be about 3i ATLAS itself, but about what 3i ATLAS might have released during its approach. If V1 Borisov is indeed a probe, it will not be the only one. Optimal mission design includes redundancy, multiple probes with complementary capabilities, distributed observation platforms that provide different viewing angles and data types. December 19th is not just a date, it is a deadline. It is the moment when years of speculation, months of observation, weeks of coordination come together in a concentrated effort to answer one simple question. What is 3i ATLAS? The answer might be simple: a comet. Unusual? Yes, but ultimately natural. obeying the same physical laws that govern every other icy body we have studied. If the December observations support this conclusion, if all the anomalies resolve into quirks of composition or geometry or observational bias, then we close the book on 3I Atlas, having learned something interesting but not paradigm-shattering about interstellar comets. Or the answer might be complicated. Complicated in ways that force us to reconsider assumptions we have held for lifetimes, that open questions we thought were purely theoretical, that confront us with evidence of intelligence operating on scales and timelines that dwarf human civilization. Either way, December 19th provides data, good data, extensive data, data that will shape our understanding regardless of which conclusion it supports. That is all we can ask from science, that it provide the tools and opportunities to test our ideas against reality and accept whatever reality teaches us. The convergence approaches, the observatories prepare, the instruments calibrate, and 3I Atlas continues its journey, indifferent to our questions, our fears, our hopes, moving according to forces we measure but do not yet fully understand, carrying secrets that December 19th might finally reveal. The 10 anomalies stack Avi Loeb compiled a list. 10 specific observations about 3I Atlas that defy comfortable explanation, that push against the boundaries of what we expect from natural objects, that together form a pattern too consistent to dismiss as coincidence or misunderstanding. Each anomaly stands on its own as something interesting, something worth investigating. Stacked together, they build a case that grows more compelling with each item added. Let us walk through them systematically, examining what each anomaly means and why it matters. Anomaly 1. The retrograde trajectory aligned within 5 degrees of the ecliptic plane. 3I Atlas moves backward relative to the planets, travelling in the opposite direction compared to Earth, Mars, Jupiter, and everything else in the solar system. Retrograde orbits are not impossible for interstellar objects. They happen. But the object's path lies almost exactly in the ecliptic plane, the flat disk where planets orbit, rather than plunging through at a steep angle as you would expect from something arriving randomly from interstellar space. The ecliptic plane is special. It contains the planets, the asteroid belt, most of the mass in the solar system aside from the Sun itself. If you were exploring another star system and wanted to study its planets, you would travel through the ecliptic plane to maximize encounters, to see as much as possible during your limited time in the system. An object on a random trajectory from interstellar space has only a small probability of arriving with such precise ecliptic alignment. Loeb calculated this probability at around 0.2%. Not impossible, but unlikely enough to notice. Anomaly 2. The sunward jet that is not an optical illusion. Most comets develop tails that point away from the Sun, driven by solar radiation pressure and solar wind pushing gas and dust outward. 3I Atlas exhibited a sunward jet during July and August, material moving toward the Sun rather than away from it. Some observers suggested this might be an anti-tail, an optical illusion caused by viewing geometry when Earth crosses through the comet's orbital plane. But detailed analysis showed the sunward jet was real, not geometric, representing actual material motion in a direction that comets do not normally produce. Sunward jets require special conditions. Either the comet is rotating in a way that vents gas toward the Sun during certain parts of its rotation cycle, or active regions exist on the Sun-facing side that produce localized outgassing. Both scenarios are possible naturally, but both are unusual, requiring specific configurations that most comets do not display. Anomaly 3. Extreme mass and velocity compared to previous interstellar objects. 1 Oumuamua, the first known interstellar visitor, had a mass estimated in the millions of tons range. 2I Borisov massed perhaps billions of tons. 3I Atlas masses tens of billions of tons, roughly 1,000 times more massive than Borisov. It also moves faster than both predecessors, exceeding 200,000 km per hour, 61 km per second, speeds that suggest a powerful gravitational kick from whatever system it came from, or substantial velocity gained through interactions with other stars during its journey. Large, massive objects travelling at high speeds are individually rare. The combination is rarer still. Loeb noted that the likelihood of observing an object this massive moving this fast, while also being the third interstellar visitor detected, is less than 0.1%. The universe is large and contains many objects. but the specific combination of properties 3i ATLAS exhibits falls into a narrow slice of parameter space that happens to be optimal for interstellar exploration. Massive objects carry more instruments, more fuel, more redundancy. High velocities reduce transit times. If you were designing a probe to visit distant star systems efficiently, you would make it massive and fast. Anomaly 4. Fine-tuned arrival timing. 3i ATLAS passed within tens of millions of kilometres of Mars, Venus and Jupiter, reaching its closest approach to Mars on October 3rd, to the Sun on October 29th, and will approach Earth most closely on December 19th. The trajectory brings it near multiple planets during a single pass, maximising observational opportunities if observation is the goal. The probability of a random interstellar object following such a path is vanishingly small. Loeb calculated it at 0.005%, a fraction so tiny that invoking chance requires accepting that we witnessed an extraordinarily rare event. Or it was not chance. Trajectories can be designed. Mission planners select paths that achieve objectives efficiently. If 3i ATLAS is a survey mission, its trajectory is brilliant, elegant, optimal. If it is a natural comet, its trajectory is a cosmological accident so improbable that it challenges our understanding of how likely events are. Anomaly 5. Extreme nickel emissions without corresponding iron. Spectroscopic observations revealed nickel in 3i ATLAS's coma at abundances far exceeding what normal comets display. Nickel is not rare in the universe, but in natural comets it typically appears alongside iron, in ratios reflecting their cosmic abundances. 3i ATLAS shows nickel without the expected iron, suggesting either a composition radically different from any comet we have studied, or a source of nickel that is not primordial material from planetary formation. Industrial alloys use nickel extensively. Stainless steel, superalloys for high-temperature applications, battery components, all rely on nickel, and often contain it in concentrations much higher than cosmic abundances. If 3i ATLAS is venting material from industrial processes rather than from ice sublimation, the nickel signature makes perfect sense. For a natural comet, it represents a composition mystery that no one has adequately explained. Anomaly 6. The cyanide to nickel ratio. Related to the previous point, 3i ATLAS exhibits a nickel to cyanide ratio orders of magnitude larger than any known comet. Cyanide, specifically hydrogen cyanide, is common in comets. It forms naturally in the cold chemistry of the outer solar system and interstellar space. Nickel is not. The extreme ratio suggests either that nickel is vastly overabundant or that cyanide is vastly underabundant relative to expectations. Either way, the composition is anomalous, inconsistent with what we understand about how comets form and what they contain. Anomaly 7. Alignment with the WOW signal. In 1977, the Big Ear radio telescope detected a strong narrowband radio signal from the direction of the constellation Sagittarius. The signal lasted 72 seconds, was never detected again, and became known as the WOW signal after the astronomer who noticed it wrote WOW on the printout. For decades, the signal remained unexplained, attributed variously to terrestrial interference, a passing satellite, or possibly an extraterrestrial transmission. 3i ATLAS's trajectory, when traced backward in time, passes within about 9 degrees of the WOW signal's origin direction. 9 degrees is not exact alignment, but it is close enough to be interesting, especially given the uncertainties in both the signal's exact source location and 3i ATLAS's precise origin point after billions of years travelling through a gravitationally complex galaxy. If the WOW signal was a beacon, and if 3i ATLAS responded to that beacon, or originated from the same source, the alignment would not be coincidental. It would be evidence of coordination, of communication, of intelligence operating across interstellar distances. This is speculative. The connection could be pure chance. 9 degrees is not that small a region of sky when you consider how many stars and systems exist within that cone, but it adds to the pattern, another improbable alignment stacked on top of others. Anomaly 8. Rapid brightening ahead of perihelion. 3i ATLAS brightened by a factor of 5 in the green band during its approach to the Sun, a change more dramatic and sudden than models predicted. Comets brighten as they approach the Sun, yes, but the increase should be smooth, predictable, following power laws based on distance and solar flux. Rapid changes suggest something activated, some process began. Operating at a different level, some energy source contributed to the brightness beyond simple solar heating. Natural comets can brighten rapidly if fresh ice gets exposed suddenly, if a crater collapses and unveils material never before touched by sunlight. But such events are transient. They fade within hours or days as the new surface gets covered by dust again. 3I Atlas's brightness increase persisted, suggesting a sustained change in activity level rather than a brief flare. Anomaly 9. No water signature in some observations. Early spectroscopy from certain instruments suggested a lack of water in 3I Atlas's coma, which is bizarre because water ice is the dominant volatile in most comets. Later observations detected water, so the discrepancy might be instrumental or geometric, observing at a time when water happened to be minimal while other gases dominated. But the initial reports raised questions about whether 3I Atlas is actually an icy body, or whether its composition differs fundamentally from what comet models assume. Anomaly 10. Non-gravitational acceleration without the required massive coma. We have discussed this extensively already. The acceleration demands massive outgassing. The outgassing should create a visible debris cloud. The debris cloud is not visible in post-perihelion images. This is the most direct contradiction, the clearest sign that something about the standard cometary model does not apply to 3I Atlas. 10 anomalies, 10 deviations from expectations, 10 data points that individually might be dismissible, but collectively form a structure, a framework, a pattern that resists natural explanation. Critics argue that cherry-picking anomalies creates false patterns, that if you look hard enough at any object, you will find things that seem unusual, that the universe is full of outliers and 3I Atlas is just another one. This argument has merit. Confirmation bias is real. We see what we look for, and if we look for anomalies, we find them. But these anomalies are not cherry-picked. They emerge from routine observations conducted by researchers who mostly assumed 3I Atlas was a comet, and were surprised when the data did not match expectations. NASA did not set out to measure non-gravitational acceleration hoping to find something weird. They measured it because that is what you do with comets, and the result contradicted comfortable assumptions. Hubble did not image 3I Atlas expecting to see unusual geometry. The telescope was pointed at the comet to get basic characterization data, and what it saw was unexpected enough to warrant detailed follow-up. The pattern exists in the data, not in the interpretation. Different researchers looking at the same data reach similar conclusions about what is unusual. That convergence suggests the anomalies are real features of the object, not artifacts of biased analysis. Stacking anomalies is valid if each anomaly is independent. If they were all consequences of a single underlying cause, stacking them would be redundant, counting the same evidence multiple times. But these anomalies are diverse. Trajectory geometry, composition, activity level, spectroscopy, photometry, temporal behavior, each comes from different types of measurements addressing different aspects of the object's nature. They are independent lines of evidence that happen to point in the same direction, towards something unusual, something that does not fit cleanly into the natural comet box. Loeb quantified the compounding improbability by multiplying the individual likelihoods. If each anomaly has a small probability of occurring by chance, say 0.2% for trajectory alignment, 0.1% for mass and velocity combination, 0.005% for fine-tuned timing, then the probability of all of them occurring simultaneously in a single object is the product of those probabilities. The result is less than 1 part in 10 quadrillion, an astronomically small number, a probability so extreme that invoking chance becomes less plausible than invoking design. 10 quadrillion is 10 to the 16th power, 1 followed by 16 zeros. For context, the number of stars in the observable universe is estimated around 10 to the 24th. The number of seconds since the Big Bang is roughly 10 to the 18. 1 part in 10 quadrillion is rare beyond normal human intuition about what rare means. Of course, rare events happen. The lottery has odds far worse than 1 in a million, yet people win lotteries. Someone has to win, and when they do, it feels miraculous to them but is merely statistical inevitability, given enough tickets sold. Similarly, the universe is vast, contains countless objects, and rare events occur somewhere simply because there are so many opportunities for them to occur. But we are not picking 3i ATLAS out of a catalogue of trillions of observed objects. We are noting that out of 3 interstellar visitors detected by humanity, the third one exhibits 10 stacked anomalies that compound to 1 in 10 quadrillion odds. That is not like winning a lottery after buying a single ticket. That is like winning 10 consecutive lotteries, each with million-to-1 odds, in a row. At some point, skepticism about low probability explanations requires more faith than accepting the obvious conclusion that something intentional is happening. If every observation points toward artificiality, if every alternative explanation requires invoking special circumstances or dismissing data, if the simplest hypothesis that explains all the facts is that 3i ATLAS is technological, then Occam's razor, the principle that simpler explanations are preferable, actually favours the technological interpretation. This is uncomfortable for many scientists. We are trained to exhaust natural explanations before considering exotic alternatives. We are taught that extraordinary claims require extraordinary evidence. We approach anomalies with skepticism because the history of science is full of supposed mysteries that dissolved into mundane phenomena once better data became available. But sometimes anomalies are real. Sometimes the data is telling us something genuinely new, something that requires updating our models, our assumptions, our worldview. The question is whether we have the intellectual courage to follow the evidence where it leads, even when it leads somewhere we did not expect and are not sure we want to go. The 10 anomalies stack. They reinforce each other. They paint a picture of an object that does not behave like natural comets behave, that occupies a parameter space incompatible with random arrival, that exhibits properties consistent with design and inconsistent with chance. December 19th offers an opportunity to add to this list, or to start subtracting from it. Observations might reveal a massive debris cloud that earlier instruments missed, resolving the 10th anomaly. Spectroscopy might show compositions that explain the nickel abundance naturally. Imaging might display surface features unmistakably cometary in origin. Any of these findings would weaken the case for artificiality. Or observations might confirm every anomaly, add new ones, pile evidence higher until denying the pattern requires willful blindness. The data will decide. That is the beauty of science. Reality does not care about our preferences. It simply is, and measurements reveal what is, and we either accept those revelations or cling to beliefs that data contradicts. The anomalies stack. 10 of them now, perhaps more later. Each one a crack in the facade of the natural comet hypothesis. Each one a hint that 3i ATLAS is something we have never encountered before, something that demands explanations more sophisticated than sublimating ice and random trajectories. We will know soon enough. The convergence approaches, and with it, clarity or deeper mystery. Either outcome advances our understanding, either conclusion is preferable to ignorance masquerading as certainty. Europa Clipper's secret transit. Between October 30th and November 6th, NASA's Europa Clipper spacecraft potentially flew directly through the ion tail of 3i ATLAS. Potentially because the agency has not confirmed the encounter publicly, has not released data, has not acknowledged that one of its flagship missions, a multi-billion-dollar spacecraft en route to Jupiter's moon Europa, passed through material from an interstellar visitor exhibiting unprecedented anomalous behaviour. The silence is deafening and deeply suspicious. Europa Clipper launched in October 2024, beginning a years-long journey to the Jupiter system where it will study Europa's subsurface ocean and assess the moon's habitability. The spacecraft carries a sophisticated suite of instruments designed to analyse composition, magnetic fields, surface features, and plume activity. Among those instruments are mass specs, the mass spectrometer for planetary exploration, capable of identifying molecules and isotopes with extreme precision, SUDA, the surface dust analyzer, which measures the composition and velocity of dust particles, and MAG, a magnetometer that maps magnetic field structures with high spatial and temporal resolution. These instruments are not idle during the cruise phase. They operate, they calibrate, they collect data on the solar wind, cosmic rays, interplanetary dust, anything the spacecraft encounters on its way to Jupiter. And in late October and early November, Europa Clipper encountered 3i ATLAS's ion tail. Ion tails form when solar wind strips electrons from neutral gas molecules escaping a comet, creating charged particles that follow magnetic field lines and stream away from the nucleus at high velocities. Unlike dust tails, which curve gently under radiation pressure, ion tails stretch straight away from the Sun, narrow and bright, visible for millions of kilometres. 3I Atlas has an ion tail. Multiple observations confirm it. The tail extends along the comet's trajectory, marking its path through space with ionized gas that glows in ultraviolet and visible light. Europa Clipper's trajectory crossed that tail. The geometry is straightforward. The spacecraft travels outward from Earth toward Jupiter. 3I Atlas moves through the inner solar system on its hyperbolic path. Their orbits intersected during the time window when 3I Atlas was near perihelion, and Europa Clipper was in the region between Earth and Mars. The spacecraft flew through the tail, potentially spending hours or days immersed in ionized interstellar material. This is unprecedented. No human spacecraft has ever sampled material from an interstellar object in situ directly, collecting particles and analysing them with onboard instruments. Europa Clipper had the opportunity to do exactly that. Mass specs could measure isotopic ratios, identifying which star system the material came from based on subtle differences in element composition that vary between stellar nurseries. SUDA could characterise dust particle size, structure, composition, determining whether 3I Atlas sheds material consistent with icy cometary dust or something else. MAG could map the magnetic field structure within the ion tail, revealing how solar wind interacts with the ionized gas, and whether any intrinsic magnetic fields from the comet itself contribute to the structure. All this data would be invaluable. It would provide ground truth, direct measurements of interstellar material rather than remote observations filtered through telescopes and spectrographs. It would answer questions about 3I Atlas's composition definitively, resolving ambiguities that plague spectroscopic analysis. It would tell us whether the nickel signature is real and abundant, whether industrial materials are present, whether the gas contains molecules we do not expect. NASA has released none of this data. The government shutdown excuse applies here too, technically. The shutdown began October 1st. Europa Clipper's tail transit occurred afterward. Data processing pipelines might be frozen. Scientists might be furloughed. All the administrative barriers that block high-rise image release could block Europa Clipper data too. But Europa Clipper is a flagship mission. It receives priority attention. Its data feeds are monitored continuously. Real-time telemetry flows from the spacecraft to ground stations, and that telemetry includes instrument status, health monitoring, basic data products that confirm everything is working correctly. Someone is watching Europa Clipper. Someone knows what the instruments detected during the tail crossing, and someone decided not to share that information publicly. The spacecraft has onboard particle detectors with immediate data downlink capabilities. These are not instruments that require months of calibration before producing useful results. They measure counts, particle fluxes, energy distributions, things that appear in raw data without extensive processing. If Europa Clipper detected unusual particle signatures, if the composition measurements showed something unexpected, mission controllers would know within hours or days of the encounter. They would also know that the public is watching 3I Atlas intensely. That speculation about the object's nature has reached levels that demand official response. That withholding data about an in-situ encounter feeds conspiracy theories and erodes trust in scientific institutions. Releasing even preliminary results from the tail transit would help. It would show transparency. It would demonstrate that NASA prioritizes science over politics. The agency has done none of that. Europa Clipper's encounter with 3I Atlas remains unacknowledged in official communications, unmentioned in press releases, absent from mission updates. It is as if the encounter did not happen, as if the spacecraft is travelling through empty space rather than through the ion tail of the most significant astronomical discovery in modern history. Why the silence? Several possibilities suggest themselves, none of them comfortable. First possibility, the data is unremarkable. Europa Clipper flew through the tail and detected exactly what you would expect from a comet. Water group ions, carbon dioxide ions, carbon monoxide ions, all in abundances consistent with natural ice sublimation. The composition matches solar system comets, aside from minor variations attributable to different formation conditions in another star system. There is no industrial signature, no nickel overabundance, no exotic molecules. Releasing this data would support the natural comet hypothesis, would undermine Loeb's speculation, would calm public anxiety about alien spacecraft. But if the data supports the natural hypothesis so cleanly, why not release it? Why let speculation fester when you have evidence that could resolve the debate immediately? NASA has every incentive to publish reassuring findings. The agency's reputation suffers when people question its honesty and transparency. Releasing data that confirms 3I Atlas is just a comet, nothing to worry about, would be the smart move politically and scientifically. Unless the data does not support that narrative. Unless Europa Clipper detected something NASA cannot easily explain, something that contradicts official statements, something that raises more questions than it answers. Second possibility, the data is anomalous but ambiguous. The instruments detected unusual signatures, perhaps nickel at higher than expected abundances, perhaps particles with sizes or structures inconsistent with typical cometary dust, perhaps magnetic field configurations that do not match natural iron tail models. But the data is noisy, incomplete, difficult to interpret without extensive calibration and cross-checking against laboratory standards. Releasing preliminary findings would invite misinterpretation, would fuel speculation beyond what the data actually supports, would create a public relations nightmare as people latch onto anomalies that might disappear with better analysis. This explanation assumes NASA is acting cautiously, responsibly, waiting until they fully understand what the instruments detected before making public statements. It is a defensible position scientifically. Premature announcements of discoveries often unravel under scrutiny, embarrassing the researchers and institutions that rush to publication. Better to be slow and correct than fast and wrong. But 3I Atlas is not a routine discovery. It is time-sensitive. The object is moving. Opportunities to observe it decrease with each passing day. Ground-based observatories planning. December observations could benefit enormously from knowing what Europa Clipper found. If the tail composition is unusual, observers can prioritize certain spectroscopic lines, can look for specific molecules, can test hypotheses suggested by the in situ measurements. Withholding that information, even if it is preliminary and uncertain, hinders the broader scientific effort. Third possibility, the data is compelling and confirms that 3I Atlas is not natural. Europa Clipper detected unambiguous evidence of industrial materials, exotic isotopic ratios inconsistent with stellar nuclear synthesis, magnetic field structures indicating internal power sources, particle compositions that have no business in a comet. The evidence is strong enough that NASA cannot dismiss it, cannot explain it away with instrument calibration issues or misunderstood natural processes. This is the possibility that keeps people up at night, the scenario that would force paradigm shifts, that would rewrite textbooks, that would confront humanity with proof that we are not alone and that our visitors are here now, in our solar system, detectable by instruments we built and launched. If this is what Europa Clipper found, NASA faces an impossible choice. Release the data and trigger global panic, religious crises, economic instability, political chaos as people grapple with the reality of extraterrestrial technology. Or withhold the data, hide behind the shutdown excuse, control the narrative until some unspecified future date when leaders decide humanity is ready for the truth. The agency has apparently chosen the second option. Whether that choice is justified depends on what the data actually shows, and without access to that data, we cannot judge. We can only note the silence, the absence of information, the gap where transparency should exist. Loeb anticipated this. He wrote about Europa Clipper's potential tail transit weeks before it occurred. He noted the scientific value of in situ measurements. He emphasized that this is data you cannot get any other way, that remote observations have limits, that direct sampling provides answers remote sensing can only guess at. His foresight makes NASA's silence more glaring. The agency knew people were watching, knew expectations existed, knew that failing to address the encounter would raise suspicions. They did it anyway. They stayed quiet. And in that quiet, speculation grows. Some researchers argue that the Europa Clipper data might take months to process, that instrument teams need time to calibrate, to validate, to write papers and submit them for peer review before making results public. This is standard practice for many missions. Data embargoes protect researchers, give them time to analyse their findings without competition, ensure that publications go through proper scientific vetting before reaching public attention. But embargoes are announced. Researchers say openly that data will be released after a specified period, that papers are in preparation, that results will appear in journals on a timeline. NASA has not announced an embargo for Europa Clipper's 3I Atlas data. The agency has not acknowledged the data exists. The silence is not about protecting scientific priority. It is about something else. The real-time telemetry capabilities of flagship missions like Europa Clipper mean that basic data products, the raw counts and measurements that instruments produce, are available almost immediately. Yes, turning those raw products into calibrated science requires work, requires time, requires expertise, but you do not need calibrated science to know whether something unusual appeared in the data. You can see anomalies in raw counts. You can spot outliers in particle fluxes. Mission scientists watching the telemetry during the tail transit would know within hours whether the encounter produced expected or unexpected results. They have had weeks now, weeks to review the data, to discuss what it means, to decide how to communicate findings. The continued silence suggests a decision was made, a choice to withhold rather than disclose, to control rather than share. This undermines trust. When institutions hide information, people assume the worst. They assume that the truth is too terrible to reveal, that officials are protecting themselves rather than the public, that transparency has been sacrificed to preserve comfortable lies. Maybe those assumptions are wrong. Maybe NASA has good reasons for staying quiet, reasons that would make sense if we knew what they knew. But we do not know what they know. That is the problem. We are left guessing, speculating, constructing narratives that might be wildly incorrect, but feel plausible given the information vacuum. Europa Clipper flew through the ion tail. That much is geometry, orbital mechanics, straightforward calculation. The spacecraft carried instruments capable of analysing what it encountered. Those instruments operated, they collected data. Someone received that data, and someone decided the public does not need to see it yet. December 19th approaches. The observational campaign intensifies. Ground-based telescopes turn toward 3I Atlas with unprecedented coordination and resources. And somewhere in NASA's archives, in computer systems accessible to a small number of authorized personnel, Europa Clipper's data waits, holding answers to questions we have been asking since July, answers that might confirm our comfortable assumptions or shatter them completely. The silence protects something. Whether it protects scientific integrity, institutional reputation, public peace of mind, or something else entirely, we cannot know without the data. All we can do is note the absence, the gap, the conspicuous missing piece in the puzzle of 3I Atlas. And we can remember that when institutions withhold information about phenomena this significant, this unprecedented, this capable of changing how we understand our place in the universe, the withholding itself becomes evidence that something important is being hidden. What that something is, we can only imagine. But imagination, unconstrained by data, tends toward extremes, toward the scenarios that institutions fear most. Perhaps that is why they stay silent. Perhaps they know that any truth they reveal will be less destabilizing than the uncertainty they create by refusing to reveal anything at all. Avi Loeb's calculation. Avi Loeb is not just calculating orbits and analysing spectra. He is receiving letters, hundreds of them, from around the world, from people who never thought about astronomy before 3I Atlas appeared, from children asking their parents for telescopes for Christmas, from engineers reconsidering their careers, from families watching the sky together and talking about what might be out there. The letters tell a story that transcends the technical details, the anomalies, the debates about whether 3I Atlas is natural or artificial. They tell a story about inspiration, about curiosity, about human beings confronting the possibility that we're not alone, and finding that possibility thrilling rather than terrifying. Charlotte Hughes from Merida, Mexico, wrote to Loeb thanking him for his work. She described how her son Marco asks about 3I Atlas news every day after school, how the boy told his parents he wants a telescope for Christmas, how a family that never cared about astronomy now follows developments eagerly, reads articles together, discusses what it means if an interstellar visitor is more than just a rock. Vladimir Shkabukin, a Canada-based engineer and CEO, wrote about how his children reacted to Loeb's work. Instead of music in the car, they asked to play Loeb's interviews. They want to know if new articles have appeared on Medium. They buy books about space and the solar system. For years, Vladimir tried to interest them in astronomy without success. One video about 3i ATLAS changed everything. His children went crazy about space, he wrote, and he cannot thank Loeb enough for giving them that sense of wonder, that curiosity, that drive to understand the universe. Guktae Kim from South Korea, a PhD in science and technology studies and senior research scientist at KAIST, wrote about intellectual courage, about the value of questioning accepted views, about how Loeb's willingness to explore unconventional ideas offers lessons not just for science, but for society, politics, economics, everything. The spirit of curiosity and creative exploration that Loeb demonstrates should remain a lasting source of inspiration, Kim wrote, and he is not alone in feeling that way. These letters matter because they reveal what is at stake beyond the technical question of what 3i ATLAS actually is. The object has become a catalyst for public engagement with science, for families talking about the cosmos, for children dreaming of becoming astronomers, for adults reconsidering what they thought they knew about reality. Whether 3i ATLAS is a comet or a spacecraft, it has already accomplished something remarkable by inspiring people to look up, to ask questions, to care about what happens beyond Earth's atmosphere. Loeb understands this. He writes not just for his colleagues, but for the public, translating technical concepts into language anyone can understand, explaining why anomalies matter, acknowledging uncertainty while refusing to dismiss possibilities simply because they challenge conventional thinking. His approach is unusual among professional astronomers. Many researchers avoid public engagement, fearing that simplifying concepts will invite misunderstanding, that engaging with speculation will damage their credibility, that wading into controversial topics will alienate funding agencies and peers. Loeb does the opposite. He publishes frequently on Medium, a platform accessible to anyone with an internet connection. He appears on podcasts, including Joe Rogan's show with its audience of millions. He writes books aimed at general readers, not just specialists. He makes himself available, answering questions, responding to criticism, explaining his reasoning in detail sufficient that non-experts can follow the logic. This accessibility matters because 3i ATLAS is not just a scientific question, it is a human question. If the object is technological, if it represents contact with another civilization, then everyone on Earth has a stake in understanding what that means. Limiting the conversation to academic journals and conference presentations excludes the vast majority of humanity from discussions that could affect our entire species. Loeb recognizes this. He democratizes the information, makes it available, trusts people to think critically about what the data shows. His calculations have been central to the technical case for artificiality. The momentum conservation analysis that determines mass loss from non-gravitational acceleration, that is Loeb's work. The probability calculations showing how unlikely 3i ATLAS's trajectory and properties are for a random natural object, Loeb did those. The cataloguing of anomalies, the systematic documentation of each deviation from expectations, Loeb compiled that list and continues updating it as new observations accumulate. But his most important contribution might be the inspiration he provides to people who want to believe that science is about curiosity rather than consensus, about following evidence rather than protecting reputations, about asking difficult questions rather than accepting easy answers. The letters he receives prove that this message resonates, that people hunger for scientists who dare to speculate, who entertain uncomfortable possibilities, who treat the public as partners in discovery rather than as children needing protection from confusing information. Loeb wrote that 3i ATLAS offers a new opportunity to attract public appreciation to science and to inspire kids to become scientists. He noted that science offers the privilege of maintaining our childhood curiosity and not pretending to be the adults in the room who know the answers in advance. This is a direct criticism of the institutional approach that dismisses speculation about artificiality before examining the evidence thoroughly, that prioritizes consensus over investigation, that values reputation over truth. The criticism has teeth, because Loeb is not a fringe figure. He chaired Harvard's astronomy department for 9 years. He directs the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He heads the Galileo Project, a serious scientific effort to search for evidence of extraterrestrial technology. He has published hundreds of peer-reviewed papers on topics ranging from black holes to cosmology to the first stars. His credentials are impeccable, his scientific contribution substantial, his standing in the community secure. When someone with that background says we should consider the possibility that 3i ATLAS is artificial, it is not crackpot speculation. It is a testable hypothesis proposed by a scientist who understands what evidence would support or refute it, who knows how to design observations that distinguish between alternatives, who accepts that he might be wrong but insists that being wrong is preferable to not looking. The institutional response has been defensive. Tom Statler's comment that 3i ATLAS very, very strongly resembles comets in just about every way dismisses Loeb's analysis without addressing the specific anomalies Loeb documents. Saying it looks like a comet is not an argument when the question is whether it behaves like a comet. Looking like something and being something are not identical when we have detailed data showing deviations from expected behaviour. Loeb addressed this in his response to Statler's statement. He noted that dismissing opinions simply because they challenge the majority view is counterproductive, that science progresses by entertaining unconventional ideas and testing them against data, that pretending to know the answer in advance is arrogance dressed as expertise. The foundation of science is humility to learn, Loeb wrote, not arrogance of expertise. This philosophical difference defines the current debate. One side argues for caution, for exhausting natural explanations before considering exotic alternatives, for maintaining consensus unless evidence overwhelmingly demands revision. The other side argues for openness, for giving uncomfortable hypotheses fair hearing, for letting data guide conclusions rather than forcing data into preferred frameworks. Both positions have merit. Science benefits from skepticism, from high standards of evidence, from resistance to premature conclusions. But science also benefits from creativity, from willingness to question assumptions, from boldness to follow implications wherever they lead. The tension between these approaches drives progress. When the balance tips too far toward consensus, science stagnates. When it tips too far toward speculation, science fragments into competing narratives disconnected from reality. 3i ATLAS tests that balance. The object presents data that is difficult to explain naturally but not yet conclusive for artificiality. The question is whether we investigate thoroughly, deploy every available resource, push observation and analysis to their limits, or whether we default to comfortable assumptions and wait for clearer cases. Loeb argues for investigation. He emphasizes that we have enough data to justify serious effort, enough anomalies to warrant careful attention, enough at stake that missing a genuine signal because we did not look hard enough would be catastrophic. If 3i ATLAS is technological, if we have evidence of extraterrestrial intelligence passing through our solar system, and if we dismiss that evidence because it challenges our worldview, then we fail as scientists and as a civilization. The letters he receives suggest that the public understands this intuitively. People want to know. They want the investigation to be thorough, transparent, honest. They want scientists to follow the evidence rather than explaining it away. They sense that something important is happening, something that could change how we see ourselves and our place in the cosmos, and they do not want that opportunity wasted because institutions prioritize stability over discovery. Loeb's calculation of the 1 in 10 quadrillion probability for all the anomalies occurring simultaneously by chance is not just a technical result, it is a challenge. It says that if you believe 3i ATLAS is natural, you are claiming that we witnessed an event so rare that it should not happen in the observable universe during the current age of the cosmos. That is a strong claim. It requires strong justification. Dismissing the analysis because it leads to uncomfortable conclusions is not justification. It is evasion. The human element of this story matters because ultimately science is a human endeavour. We do science, we fund science, we care about science because it helps us understand the world and make better decisions. When scientific institutions lose public trust by withholding information or dismissing legitimate questions, they damage their ability to serve that function. When individual scientists like Loeb bridge the gap between technical expertise and public understanding, they strengthen science by showing that it welcomes participation, values curiosity, respects people enough to share difficult truths. 3i ATLAS has inspired children to want telescopes. It has brought families together to discuss the universe. It has reminded adults that wonder is not just for childhood, that asking whether we are alone remains one of the most profound questions we can contemplate. These outcomes are valuable regardless of what 3i ATLAS turns out to be, because they represent renewed engagement with science, renewed appreciation for what science can teach us. Loeb's calculation stands. The probability is vanishingly small. The anomalies are real. The pattern demands explanation. Whether that explanation involves natural processes we have not yet understood, or technological artifacts from another civilization, the investigation must continue, must accelerate, must produce answers before 3i ATLAS leaves the solar system forever. And throughout that investigation, the letters will keep coming. People will keep writing to say thank you for inspiring them, for treating them as intelligent partners in discovery, for daring to ask questions that matter. Because in the end, that is what science is supposed to do. It is supposed to inspire, to provoke thought, to expand our understanding of what is possible. 3i ATLAS does that. And Avi Loeb, by refusing to settle for easy answers, by calculating the improbabilities and documenting the anomalies and inviting public engagement, ensures that the inspiration continues, that the questions get asked, that we do not miss this opportunity to learn something profound about our universe and ourselves. The calculation is technical, the implications are human, and the intersection of those two realities defines why this matters, why we should care, why December 19th represents not just another observational opportunity, but a moment when science serves its highest purpose, answering questions that touch the deepest parts of what it means to be a conscious being, looking up at the stars and wondering what looks back. The probe theory unraveled. Let us connect the pieces, all of them, every data point, every anomaly, every observation that has accumulated since July. Let us build the picture that emerges when you stop forcing the data to fit comfortable assumptions and instead let the data speak for itself. 3i ATLAS is not a comet. It is a mothership, a massive technological construct from another star system, travelling through our solar system on a carefully designed trajectory that maximizes observational opportunities while minimizing detection risk. It arrived from interstellar space, timed its perihelion to coincide with solar conjunction from Earth's perspective, deployed smaller probes during that window when human telescopes could not observe it directly, and continues outward on a path that will take it past Jupiter before leaving the solar system forever. V1 Borisov is one of those probes. Deployed on November 2nd or shortly before, discovered 4 days after 3i ATLAS completed perihelion, positioned directly between the mothership and Earth. It exhibits a nucleus without a significant tail, characteristics inconsistent with natural comets at its solar distance. It travelled along a trajectory that brought it within 103 million kilometres of Earth on November 11th, optimal for close-range observation of our planet, our civilization, our technological signatures. The mass loss patterns support this interpretation. 3i ATLAS lost over 13% of its mass during perihelion. That mass did not spread into a visible debris cloud. It remained coherent, travelling on specific trajectories. V1 Borisov accounts for part of that mass. Other probes, not yet discovered or not yet recognised as distinct objects, account for the rest. The mothership shed its scouts, its observation platforms, its instruments, and they dispersed to predetermined positions throughout the inner solar system. This is not speculation pulled from science fiction. This is inference from data. When an object exhibits non-gravitational acceleration requiring massive mass loss, and when that mass loss produces no visible debris cloud, the mass went somewhere specific. When a second object appears between the primary object and Earth immediately after the primary object reaches perihelion, and when that second object displays unusual characteristics for its class, connecting the two is not wild theorizing, it is pattern recognition. The Oberth effect explains why perihelion is optimal for probe deployment. At that point, 3i ATLAS was moving fastest, experiencing maximum solar gravity, positioned perfectly for using gravitational assists to send probes toward different destinations with minimal fuel expenditure. An intelligence designing a survey mission would choose exactly that moment for deployments. The timing maximizes efficiency, provides maximum flexibility for probe trajectories, takes advantage of orbital mechanics to achieve what would otherwise require enormous propulsion capability. Earth was the primary target. Had to be. 3i ATLAS's trajectory brought it close to Mars, but Mars is a dead world, geologically inert aside from seasonal dust storms, atmospherically thin, devoid of obvious technological signatures. Venus is hostile, its surface hidden beneath opaque clouds, its extreme temperatures and pressures making surface observation nearly impossible. Jupiter is distant, a gas giant with no surface, interesting for its moons but not for indigenous technology. Earth is different. Earth has oxygen in its atmosphere, a biosignature detectable across interstellar distances. Earth has radio emissions, television broadcasts, radar pulses, everything we have been transmitting into space for over a century, announcing our presence to anyone capable of listening. Earth has cities visible in nighttime photography, artificial light on the dark side, patterns of illumination that natural processes do not create. Earth is where the intelligence is, where the technology exists, where something worth investigating has developed. 3i ATLAS came to look at us. That is the hypothesis that fits the data. It approached along a trajectory aligned with the ecliptic plane, maximizing time near planetary orbits. It fine-tuned its arrival to pass near multiple planets during a single visit. It deployed probes during perihelion when it was closest to the Sun and moving fastest. One of those probes positioned itself between the mothership and Earth, achieving close approach on November 11th. Another probe, or perhaps the same one continuing its mission, will be in position on December 19th when 3i ATLAS makes its closest approach to our planet. The March 16, 2026 Jupiter flyby is the next major event. 3i ATLAS will pass within 54 million kilometers of Jupiter, close enough for detailed observations of the gas giant and its moons. This could be a secondary objective, studying the largest planet in the solar system, examining its magnetosphere and radiation environment, observing the volcanic activity on Io, or the subsurface ocean on Europa. Or it could be a gravitational assist, using Jupiter's immense gravity to adjust trajectory for the final exit from the solar system, sending the mothership on a specific outbound vector that points toward its next destination. Because 3i ATLAS is not just visiting, it is travelling. It has been travelling for billions of years, crossing the galaxy, hopping from star system to star system, conducting surveys, gathering data, perhaps reporting back to a home civilization, or perhaps operating autonomously, a machine intelligence programmed to explore and learn and continue forever. Its trajectory through our system is one stop on a journey that spans timescales longer than human civilization, longer than our species has existed, longer than multicellular life has flourished on Earth. This is what the numbers tell us. This is what the probabilities demand we consider seriously. 1 in 10 quadrillion odds, for all the anomalies occurring naturally by chance. That number is not metaphorical. It is a quantitative assessment based on measured probabilities, calculated from data, representing the compounded unlikelihood of everything we observe fitting together coincidentally. Invoking chance at those odds is faith, not science. Accepting that we are witnessing something intentional, something designed, something technological, is the scientifically defensible position when the evidence points overwhelmingly in that direction, and natural explanations require assuming multiple independent improbable events all happened simultaneously. The probe theory unifies everything. It explains why 3i ATLAS exhibits non-gravitational acceleration without a visible debris cloud. The acceleration is thrust. The missing debris is deployed hardware. It explains why V1 Borisov appeared where it did when it did, intentional positioning rather than cosmic coincidence. It explains the blue colour shift during perihelion, engine operation or power system activation. It explains the missing tail post-perihelion, no random outgassing because nothing is outgassing randomly, everything is controlled. It explains the trajectory alignment with the ecliptic plane, deliberate navigation rather than chance arrival. It explains the fine-tuned timing past multiple planets, mission planning rather than gravitational accident. Every anomaly resolves, every contradiction disappears. The picture becomes clear once you accept the framework that the data has been suggesting since July, but that institutional astronomy refuses to acknowledge, because acknowledging it means accepting conclusions that overturn comfortable assumptions about our uniqueness, our isolation, our security in a universe we thought was empty of intelligence except for us. We are not alone. That is what 3i ATLAS tells us. We are being visited. We are being observed. And our visitors are sophisticated enough to design trajectories that optimize their objectives. patient enough to spend billions of years travelling between stars, interested, enough in what they find here to deploy probes for close examination. Should we be afraid? Loeb addressed this in one of his conversations. He was asked directly, "Are we screwed?" His answer was nuanced. Yes, if we are visited by a technological civilization more advanced than ours, because they move 3 times faster than our fastest rocket, and they are 50 times larger than Starship, and we cannot cope with that. But if we survive such an encounter, it should fill us with humility. It means we have siblings in the family of intelligent civilizations more accomplished than we are. That should inspire us to do better, not make us jealous. He ended with a nervous laugh and a warning. Let us just hope we do not meet a serial killer on this blind date. That warning is not alarmist. It is realistic. We know nothing about the intentions behind 3i ATLAS. We infer that it is technological based on anomalies in its behaviour. We calculate that its trajectory was likely designed rather than random. But we have no information about why it is here, what it wants, how it will interact with us if interaction occurs at all. The universe contains possibilities beyond our imagination. Some of those possibilities are wonderful. First contact with benevolent explorers, exchange of knowledge, partnership with civilizations that have solved problems we struggle with, inspiration to become better versions of ourselves. Other possibilities are terrifying: exploitation, invasion, indifference to our existence, casual destruction, because we are in the way of something they value more than our survival. We do not know which scenario we face. The data tells us that something is here, something intelligent, something capable of interstellar travel and sophisticated enough to navigate our solar system with precision we can barely achieve within our own planetary neighbourhood. What that something intends remains unknown. December 19th might provide clues. Ground-based observations could detect signals, radio transmissions, optical flashes, modulated light curves, anything that indicates intentional communication. The absence of such signals would not disprove the technological hypothesis. Advanced civilizations might operate in frequency bands or using protocols we cannot detect, but their presence would confirm it definitively, or we might see nothing unusual. 3i ATLAS might continue behaving as it has, accelerating without visible outgassing, displaying no tail despite physics demanding one, moving along its predetermined trajectory without acknowledging our existence. In that case, we are left with data but no contact, evidence but no interaction, knowledge that we are not alone but no understanding of what that knowledge means for our future. The probe theory unravelled is both exhilarating and unsettling. Exhilarating because it suggests we live in a universe rich with intelligence, where civilizations arise and build and explore and endure for timescales that dwarf our own history. Unsettling because it confronts us with our insignificance, our technological infancy, our vulnerability to forces we cannot control or even fully perceive. 3i ATLAS and its probes, if that is indeed what V1, Borisov and potentially other undiscovered objects are, represent a threshold, a line we cross from being alone to being observed, from isolation to contact, from thinking ourselves unique to knowing ourselves as one among many. Crossing that threshold changes everything. It changes how we see ourselves, how we prioritize our efforts, how we think about our place in cosmic history. We stand at that threshold now. The data is in. The anomalies are documented. The pattern is clear. What remains is acceptance, acknowledgement that the comfortable universe we thought we inhabited was an illusion, that reality is stranger and more complex and more populated than we imagined. V1, Borisov sits between 3i ATLAS and Earth. It watches, it measures, it records, and somewhere in the data streams flowing between the probe and the mothership, in communication channels we cannot intercept using languages we cannot decode, information about us travels outward, away from the sun, toward whatever star system 3i ATLAS will visit next, carrying news of Earth, of humanity, of the civilization that builds telescopes and launches spacecraft and asks whether it is alone. The answer to that question arrived on July 1st, when ATLAS telescopes first detected 3i ATLAS. It deployed itself into our awareness on November 2nd, when Gennady Borisov found the object we now call von Borisov. It will become undeniable on December 19th, when the convergence brings 3i ATLAS to its closest approach, and observations either confirm the natural hypothesis through overwhelming contradictory evidence, or cement the technological hypothesis by eliminating every remaining alternative. The probe theory is not fringe speculation. It is the simplest explanation that accounts for all the data. Occam's razor, properly applied, favours it over natural hypotheses that require invoking multiple independent improbable events. The burden of proof has shifted. Those who insist 3I Atlas is natural must now explain how nature produces objects with 1 in 10 quadrillion odds, how coincidence stacks so perfectly, how randomness creates patterns indistinguishable from design. They cannot, not convincingly. Not without abandoning the same statistical reasoning we apply to every other domain of science. And so the probe theory stands, awaiting disproof that has not come, accumulating support as each new observation adds to the pattern, rather than contradicting it. We are not alone. 3I Atlas proves it. V1 Borisov confirms it. December 19th will reveal how much more there is to learn about visitors who travel between stars to study worlds like ours, to observe civilizations like humanity, to gather data about the diversity of intelligence that evolution produces when given billions of years and suitable environments. This is the most important story in human history. It deserves the best science we can bring to it, the most rigorous observations, the most honest analysis, the most transparent communication of what we find. Anything less is failure, a squandering of opportunity that will not come again in our lifetimes, or perhaps in many generations. The probe theory unravelled, the pieces connected, the picture clear. Now we wait for December 19th and whatever revelations that convergence brings, knowing that regardless of what we find, we have already crossed the threshold from isolation to awareness, from alone to accompanied, from wondering to knowing. The universe is not empty. It never was. And 3I Atlas, with its probes dispersed through our solar system, makes that truth impossible to ignore any longer. Welcome to the new reality. We have company, and they are watching.